I just remembered to hit record, so good morning, Astronomy 1010. We are about to do Homework 7, Lecture 9, Lab 8. And Homework 7 has questions from Chapter 14 and Chapter 7. And Olivia is going to take us out with Chapter 14. Olivia, I'm having focus issues here. So I need to, I need to open up the Logitech capture. For some reason, I've turned off autofocus, but I have to open up the Logitech camera app so that it remembers that autofocus should be turned off. I don't know why it does that, but it's extremely irritating. Autofocus is clearly off. There we go. All right. All right, so that should fix us here. Okay, sorry about that. Chapter 14, number 50.
Okay, so chapter 14, number 50, solar energy output.
Okay.
Observations over the past centuries show that the sun's visible light output varies by less than 1%, but its X-ray output can vary by a factor of 10 or more. Explain why changes in X-ray output can be so much larger than those in the output of visible light.
What does the sun give off more of, X-rays or visible light?
X-rays?
No.
No, visible light.
Yeah, that's tricky what this question is asking here. Hold on, I need a stool. Let's take a look at the black body profile spectrum for the sun together. It would be nice if that lecture was still open, but okay. We should also call up our radiation. Okay, you'll remember that last time in our lectures, we learned that there are certain objects that glow due to temperature alone. And these objects are what are called black bodies. And black bodies emit light at all wavelengths of the electromagnetic spectrum, but there's always one wavelength that they emit more than any others. And that's called lambda max. It's the peak wavelength of emission. In the case of our sun, the photosphere glows as a black body. And it's a black body whose temperature is very close to 6,000 Kelvin. It's 5,800 Kelvin. And that means if you actually look at the real spectrum of the sun, which is shown here in slide 53, this is a dual plot of two different graphs. The black line represents the true spectrum of the sun. The green line represents the spectrum of an ideal black body whose temperature is 5,800 Kelvin. You'll notice there's very good agreement between a pure black body and the spectrum of the sun. The sun is almost a black body. There are a few deviations, however. That's because the sun actually produces an absorption spectrum. And these small dips, excuse me, I'm going to sneeze. Okay. These small dips that you see here, these are called absorption lines. And the sun's spectrum actually looks more like an absorption spectrum. But ignoring that for a moment, the sun is approximately emitting a black body, and it's glowing because of its temperature. You'll notice the peak falls at what wavelength, students? What's the wavelength of peak emission of this graph? I just want to see if you can read the graphical data. That's one of the skills I'm supposed to teach you as your science professor.
Would it be like close to 500 nanometers?
Very
Like around
good.
there?
Yeah, in fact, it's damn close to 500 nanometers. And what part of the electromagnetic spectrum is that found in? No?
I'm trying to remember from last.
Do you want a
from 2
cheat
days
sheet?
ago. Yeah, I'll look. I'll check.
Wait, I've got a cheat sheet right here. You can just look at my screen. There's too many things going on over here. Get out of here, loser. You weren't there to help me when I needed you. Slide 63. Where's 500 nanometers?
It's it's blue or like teal.
Teal. Okay, fine. But it's clearly in the visible regime, right?
Yes.
X-rays are over here, right? Where would X-rays be on this graph?
Would it be in like the beginning of it, or like the
Yeah.
200
Like if
or
I use my
around
box,
there?
X-rays would be like over here, right?
Yeah, in the very beginning. Yeah.
So there's the X-rays, and there's the visible light. Well, close to that anyways. So what does the sun give off more of, X-rays or visible light?
Visible light.
Way more visible light. So then I'm confused. What the hell is this question asking me then, Olivia? Because I thought the question said, why does the sun give off 10 times more X-rays than visible light? But it must not have asked that, huh? Wait, you're muted.
Sorry, I always forget that. So the question said, oh yeah, it does say that.
No,
Yeah,
it doesn't.
No, over the
It
past
says something else.
century, sun's visible light output varies by less than 1%, but its X-ray output can vary by a factor of 10 or more.
So what's the difference between what this question is asking and what we were just talking about? Feel free to chime in and help her, class.
Yeah, I don't know. X-ray output can vary by a factor of 10 or more.
We were just talking about the comparison between those two, but the question is asking more to compare them to themselves at an earlier time.
You're almost there, Adrian. You're almost there. You're so close. It's not about, it is sort of about comparing them to themselves, but it's not at an earlier time.
Or at least at a different time.
I think you're trying to say the right thing. I just didn't like it. The key part of that question is varies as. They're not asking you about the total emission. They're asking you about the variability in emission. And because that's difficult for us to understand, I think we need to start by drawing a little sketch of what the question is asking us so you can understand, okay? So let's start by making a sketch of the output of these two types of light over the last 100 years. So what I'm going to do is I'm going to make a y-axis, and then I'm going to make an x-axis. And on the y-axis, we're going to plot the brightness of light, say in watts per square meter. So I'm plotting the brightness in watts per square meter. And on the x-axis, I'm going to plot time in years, over 100 years from, say, 1900 to the year 2000. I'm going to use black for visible light and blue for X-rays, but if you guys only have a pencil, you might want to use a dotted line and a dashed line or something. So here's the visible light. The visible light is mostly steady with only small wiggles at the 1% level. The X-ray light, however, is definitely less than the visible light. We saw that from the graph with Olivia, but the variability in the X-rays is much greater. So for instance, we'll see spikes and changes in X-rays. In particular, they seem to have an 11-year period. Which I didn't faithfully reproduce, but whatever. And what they're trying to say is the maximum X-ray emission is 10 times, a factor of 10 times greater than the minimum X-ray emission. One thing that's awkward about this 10 times is that here we're comparing a percentage. The max and min fluctuates by 1%. Here we're fluctuating by a factor of 10. It might be less awkward if both of those had the same, well, neither one of them have units, but they should at least be in the same format. So what would the number 10 be as a percentage, students? Any number can be considered a percentage if you want to. What is the number 10 expressed as a percentage?
Oh, percentage, 10%.
10%.
Pardon?
10%, because
No. All right, let's try this a different way. What is this number as a percentage?
50%.
Good. What's this number as a percentage? Keep going, Jennifer.
Oh, 100%. I
Well-
mean, 25%.
Wait, that's a 7.
Okay.
Help?
75%?
Okay. What's this number as a percentage?
100%.
What's this number as a percentage?
200%.
What's this number as a percentage?
1000%.
Good. In other words, if you compare the variability in X-rays to the variability of visible light, it may be that there is more visible light coming from the sun, but there's 1,000 times greater variation in X-ray output, max to min, than there is variation in visible light, max to min. That's what the question was asking, Olivia. But we have to be able to extract that. We have to be careful to pay close attention to every little word and extract meaning from it. Do you see what I mean? We always in science have to do a very close reading of the text. Okay, I want this in your homework because this explains what the question's asking. Now we got to try to explain it. Why the hell do you think there'd be 10 times more variation in variability in X-ray emission compared to variability in visible light emission? I wonder what parts of the sun, these two types of emission come from. Let's look at our layers of the sun together. Last time I taught you that there were different layers of the sun. Where do you think the X-rays are coming from? Where do you think the visible light is coming from? You could consult your notes.
Off the top of my head, before I look at my notes, I just wanted to guess.
Yes. Guessing is fun.
X-ray sounds like it would come from the radiation zone, but I don't know if that would be correct because that's like inner.
Unfortunately not. Let me start by giving you a hint. Anything down here does not directly emit light into space. That stuff is all, these three layers, the core, the radiation zone, and the convection zone, are hidden from us. So that's one thing to think about. The first layer that can actually shine into space towards Earth is the photosphere. We can also detect light from the chromosphere and the corona, but we cannot directly image light from the convection zone because the gas is too thick and the light cannot escape from there.
So would the photosphere give off the light?
What type of light? There's two types of light here.
Right, visible light, I meant.
That's right. The photosphere is responsible for the visible light. Well, what's producing the X-rays? Something I didn't do last time is I didn't explain how, I didn't really do a good explanation of explaining how the magnetic storms work on the surface of the sun. So here's a picture of the sun where you can see all of the twisting, winding magnetic fields. And you're actually looking at 17 nanometers, which is wicked, wicked close to the X-ray portion of the spectrum. It might as well be X-rays, okay? When you look at the sun in X-ray light, you see some wild looking things. You see some crazy magnetic field lines. You also see bright X-ray emission where the magnetic field lines are the most intense. But look at the surface of the sun in this picture, or in this video. In this video, what color is the surface of the sun? Sorry, Olivia, you're muted.
It's black.
Yeah, it's black. What does that mean? Black is the absence of color, right? It means, Olivia, that when you're looking at the sun here, the surface, which is the photosphere, is black because it's not giving off any X-rays. The X-rays are only coming from the magnetic field activity. In reality, what's happening is the type of light that's being produced is what the Germans call Bremsstrahlung radiation, or braking radiation. And in the upper layers of the sun, let me try to, I need my drawing, I'm going to use the whiteboard tool here, which I don't often use. Okay, so let's imagine we have the sun. I'm going to try to do all the drawings here. Let's see if it comes out any fun. So here's the sun. Well, I guess I could have done that better. Okay. And let's draw some magnetic field lines coming out of the sun. We'll make the magnetic field lines green just for the heck of it, okay? And you guys can see the magnetic field lines are kind of doing things like this. They're making those loops, right? Well, if you have a small charged particle, such as an electron, I like to use blue for electrons. Here's a little negatively charged electron. Oh, this is fun. I'm having a grand old time. Let's put a little minus sign on it. Okay, there we go. And the electrons are very, very, very high temperature. So they have extremely high kinetic energies, and they're flying through the atmosphere of the sun at something close to the speed of light. So there's my electron. And they're flying at super, super high velocities towards the magnetic fields. And that means they have kinetic energy. When they strike the magnetic field captures the electron like a fly stuck to fly paper, and it reduces its kinetic energy. But in order to reduce its kinetic energy, it has to emit that energy in the form of a very short wavelength, very high energy photon, which is usually in the X-ray portion of the spectrum. So when you look at the sun in X-rays, the surface is dark because the thermal radiation doesn't produce a lot of X-rays. Where we see the X-rays from is from the electrons. Now this is just one electron, but you have to imagine that there's billions upon billions and billions of electrons all striking these magnetic field lines. And every time they hit the magnetic field lines, they produce an X-ray. I can show you a little model of what this might look like if I use the physics Java apps. Now, they didn't intend this app for this purpose, but I've bastardized it I don't know what the right word is. I've used it for my own nefarious purposes. Wait, here we go. So this happens to be a proton, but you can get bremsstrahlung from either particles. Let's give them a velocity of, I don't know, 75% the speed of light. Now, I guess, can I draw the magnetic field line here without screwing this up? Let's try that. Here we go. I'm going to attempt to draw the magnetic field line. Oh, I guess it doesn't want, this is a flash application, so it doesn't like when I do that. Okay, fine. So I'm just going to stop the charge. Imagine it hits an invisible magnetic field line. Boop. Can you see that little kink in the electric field? That's the emission of a really short wavelength, very high energy X-ray. That's bremsstrahlung radiation right there. Boop. It's called bremsstrahlung radiation. Now, when we see those cool movies of the sun, I guess I have to stop share and then reshare my screen. All of that emission that you're seeing here is all bremsstrahlung radiation. And when we really get a spike in it, you'll notice that during a solar flare, which you're about to see here, watch this. You get a huge burst of X-rays during solar flares when there's, whoa, did you see that huge eruption there? That's a massive solar flare. And you can see some of those in some of the thermonuclear art videos. You'll remember there's this cool YouTube thermonuclear art. And they occasionally show you some very massive solar flares. Now, in this video, they're changing their wavelength of observation. Anytime you see it look yellow, that's basically X-rays. But these are other wavelengths. All right, let's, no thanks. This is very high resolution, so let's get rid of this. Let's see if we can find one of the solar flares. I think around here. Woo! Did you see that? That basically looks like a crazy, it looks like lightning, but it's not lightning, it's plasma and it's magnetic fields. It's similar to lightning in a way. I just wanted to see if we could get another burst or another solar flare here. This is all X-ray emission. Look at how high resolution this is. So what do you think, guys? What does this tell us about why the visible light varies by 1% and the X-ray light varies by a factor of 1,000 or 1,000%?
I want to say something like, I mean, I don't know if this is correct, but like because the amount of like when the solar flare happens is like so much stronger than maybe visible light or something, that it shoots more X-ray out or something.
Yeah.
I don't know how to exactly word it, but something along those lines.
That's pretty close, Olivia. That's not too far at all. I know no one bought the book this semester, and I understand why, but since we didn't buy the book, and since we most certainly did not read the book, let's have me read the book to you. Just one passage, just one quick passage. And this passage in the book is called Solar Storms. And it shows some pictures of magnetic fields and of these giant X-ray emissions, right? This is just one paragraph I want to read to you. It's like one sentence long. The magnetic fields winding through sunspots and prominences sometimes undergo dramatic and sudden change, producing short-lived but intense storms on the sun. The most dramatic of these storms are solar flares, which emit bursts of ultraviolet light and X-rays along with charged particles into space. In other words, that burst of X-rays is coming from those solar flares and those magnetic eruptions in the sun, which is sort of what you said, right? Let me help you refine your answer and put it into a better form. So let's all write together now. Okay, we will write X-ray output from the sun is so much more variable than visible light output. Sorry, I don't need a comma there. X-ray output from the sun is so much more variable than visible light output because the X-rays are produced in different layers by different processes. All right, now we're going to get into the two different types. We're going to hit hard return and start a new paragraph here. X-rays are produced at the sun's corona, or let's say in the sun's corona. Let's underline the key terms here. X-rays are produced in the corona by something called, okay, the German name for it, the name the physicists use, is Bremsstrahlung radiation. And this is a crazy ass German word with a crazy ass German spelling. So let's see if we can do this one together. Go easy on me, guys. My German isn't very good. Bremsstrahl. I remember there's like a double letter somewhere unpredictable. Okay, it's two S's. Bremsstrahlung. It means braking radiation, like you're slamming the brakes on the electron. By Bremsstrahlung, by Bremsstrahlung radiation, where charged particles are captured by magnetic field lines where charged particles are captured by magnetic field lines and emit X-rays. In other words, students, this light is non-thermal. This is not black body radiation. Because the magnetic fields fluctuate, with solar storms and in particular the 11-year solar magnetic cycle. Let's underline solar magnetic cycle because that's a big concept. Because the magnetic field lines fluctuate with solar storms and the 11-year solar magnetic cycle, so does X-ray output. I should put a comma there. So does X-ray output fluctuate. Now we've explained the X-ray bit. Let's explain the visible light bit. Visible light, on the other hand, is produced at the sun's photosphere by thermal blackbody radiation. We will say because the temperature of the photosphere remains constant. Okay, I was trying to get this all on one board, but I've screwed it up. I'm gonna have to go back up here, sorry. Because the temperature of the photosphere remains constant at 5800 Kelvin, so does the emission of visible light remain constant with only a 1% variation due to blank. I wanted to see if you guys could fill in the blank. What could be causing the 1% variation in visible light? What in the world could be producing the 1% variation in visible light that we see, at the sun's photosphere? What could be causing very small changes in the emission of visible light that changes over time?
Does it have to do with those black dots on the surface?
Maybe, yeah. Maybe it does. What are them black dots called?
I know, I'm trying to remember. I kind of forget.
No one remembers the names of those. Pardon, Andrew?
Would it be sunspots?
Yes, sir. The sunspots are blocking tiny little bits of visible light. Okay, guys, take a moment to finish that up. While I heat up a cup of coffee, it'll take me 45 seconds. Peanut M&Ms. All right. Someone's being naughty this morning. All right. Are we all good here? Can I erase? Let's try the next problem. Number 55. Janabelle, can you read that for me with your newly found voice?
Is it chemical burning in the sun? Okay.
Yes, ma'am.
When an object burns in a fire, the amount of energy released through this chemical burning is typically about 10 to the 8th power joules per kilogram of mass burned. Use this fact to estimate how long the sun will last if its energy source were a huge fire releasing chemical energy rather than its actual source, fusion energy.
Okay. This problem attempts to explain why the sun, these look like chili peppers, is not a ball of fire. Fire is a chemical reaction. It's not a nuclear reaction, it's a chemical reaction. And in theory, you could imagine a giant ball that would mix oxygen and, say, methane and produce fire. And if you did so, how long could that ball last? Well, let's remember that ball has a mass. The mass of the sun is 2 times 10 to the 30 kilograms. Let's also remember that that ball has a light output, which is constant, at 4 times 10 to the 26 watts. The name of the game, students, is to take these 3 numbers. Imagine that you had a ball the same mass as the sun that has to pump out the same amount of light that the sun has, but instead of using nuclear fusion, it's using chemical reactions like fire. Fire releases 10 to the power of 8 joules for every kilogram of matter that you burn. The question we want is to ask, how long could this fireball shine? And how would it compare to the age of the sun and the age of the earth? What do you think we should do? There's no real formula for this. You just have to think and use dimensional analysis. Anyone have any ideas about how we might get started here? These peanut M&Ms kind of taste like dog fur. Well, let's think about it in terms of units, which is what I was suggesting to do. What units should our final answer have? like when I am done with the problem and I have an answer, what will the units of that answer be?
I want to say joule or watts because I don't know, because kilograms would, well, no, I don't know. I'm just kind of looking at the units like on the board.
Well, we are going to want to look at these units, Olivia, but let's just start by you're overthinking this problem. Let's just make it real simple.
Okay.
If the question is how long, what units should I have at the end?
Would it be like a time?
Yeah. Give me a unit of time.
Seconds?
Sure. I'd like to have units of seconds at the end. Is there anything in the units that we have, Olivia, that could give me seconds? Can I get seconds out of any of these units?
Watts?
Yeah. How do I get seconds from watts again? This is a distraction. Let's get rid of that. How do watts give me seconds, Olivia?
I'm trying to look in my notes.
Yeah. Someone's got to remember what's a watt. What's a watt?
One watt equals 1 joule per second.
Aha. Now that's what I need to hear. Okay, so this is the same as, I'm going to start putting my units in red. 4 times 10 to the 26 joules per second. Okay, this is how the game is going to work, Olivia, and anyone else who wants to play. We're going to have some division bars, and we got to try to put, this is how I'm teaching you how a scientist solves problems. This is how a real live scientist, a wriggling, squirming scientist would solve a problem like this. They would ask themselves, how can I jiggle around these numbers and units in such a way that I end up with seconds? Because here's the idea. If the final units come out as seconds, then I have to have figured out how long. It's just that simple. So Olivia, you've got joules per second, joules per kilogram, and kilograms. How can you arrange those numbers in such a way to end up with seconds?
Well, in the last, I know this is probably jumping ahead, but like the last division bar, seconds would go on the bottom.
But wait, if seconds go on the bottom, how are they going to end up on the top?
Oh, the top, sorry.
Okay, fine. So you want to put seconds on the top.
I'm just trying to think backwards, I guess.
Yeah, that's exactly how you're supposed to solve a problem, by thinking backwards. Okay, so I put seconds on the top. What else?
Joules on the bottom.
Yeah, because the seconds and the joules are glued together by that number. Okay, fine. So where would the number go then?
It would be, what did I say? 1 joule per second.
No. That's the number that glues the joules and the seconds together. You got to use that number.
Okay.
Where does it go?
On the top?
No,
No,
that would be 4 times 10 to the 26 seconds equals 1 joule. That's not what this says. This says there are 4 times 10 to the 26 joules per 1 second, right?
Okay, so 1 on the top and then 4 times 10 to the 26 on the bottom.
Exactly.
Okay.
Okay, you've actually done 33% of this problem. You want to do the other 66% while you're at it?
I can try.
All right. Keep trying.
Okay.
No one's talking to me, so we'll have you talk to me.
Oh, okay. So then joules would have to go on the
Yes.
top of the middle division bar.
That's true. If you don't do that, you won't be able to cancel them out.
Mm-hmm.
Okay, but where are joules connected to other things in this givens here?
Kilograms?
So kilograms will have to go in the bottom.
Yep.
And now put the numbers in.
It would be 10 to the 8th on the top. Would it be on the top?
Yes, because it's 10 to the 8 joules
Yep. And then I guess 1 kilogram on the bottom.
per 1 kilogram, yeah. All right, now what?
Okay. Would watts have to go in there at some, or no, not
Or
at all?
to use watts.
Oh, that's right. Okay, that's right.
Right now, your problem is that you've got seconds per kilogram, but you really want seconds.
So would kilograms go on the top of the first one?
Yeah.
The first division bar?
So
And
what do I put in for
then-
numbers?
1, would it be 1 kilogram? Or no?
The
No,
sun is more than-
2
Yeah.
times 10 to the 30.
That's
To
right.
the, yeah. And then 1,
No, you wouldn't put anything on the bottom.
oh, that'd be it. Okay.
Because this is just kilograms. It's not kilograms per something.
For
you know?
anything. Okay, that makes sense.
And that's how dimensional analysis works. You just jiggle all the numbers and the units around until you end up with time. So apparently, if we take the mass of the sun and we multiply it by the number of joules per kilogram, that gives me the number of joules that the sun can produce. And then I divide it by the amount of energy it's releasing to find out how many seconds it can shine. Oh, now it makes sense to me because the units make sense. Units first, think later, okay? That's the moral of the story. So, punch them up. Hey, how do you put 10 to the 8 in your calculator? Because I already know you guys are going to botch this somehow. How do I put 10 to the 8 inside my calculator?
Would you do 10 and then the button that has like the X and
Hell
Y?
fucking no, you wouldn't. That's what I was afraid you were going to say. Look,
Oh, sorry.
can you get something straight? This button means times 10. If you say 10 exp8, that's the same thing. Wait, clear. If you say 10 exp8, that is essentially the same thing as saying 1 exp9. Because 10 times 10 to the 8 is 1 times 10 to the 9. Here, you know what? I think you guys unfortunately need training wheels. 10 to the 8 is not okay for you. We're going to have to do 1 times 10 to the 8 until you learn how to not fall off your bicycle, okay? Not 10 times 10 to the 8. 1 times 10 to the 8. Just give me the answer.
Is it 10 million or 10 to the 6? Or 10 times
I got a much bigger number than that. Wait, who's talking to me right now? Is that Nick? Oh, sorry.
Yes.
Yeah, Nick, you're always so quiet for some reason. Nick, can you punch that one more time for me? I got a much bigger number than 10 million. At least in terms of seconds. I guess I can't really see. If we were live together, Nick, I could see what you were up to.
Oh, this time I got 100 million.
All right, here. Nick, watch me. Bit of punch together, okay? We're going to do 2 exp30 times 1 exp8 divided by 4 exp26. What do you get now?
5 to the 11. I have absolutely no idea what I did wrong before.
Yeah. I knew your answer couldn't be right because you were multiplying by 10 to the power of 30, right? So 5 times 10 to the 11. Why don't we convert this to years? And I think I can help by reminding you that 1 year is equal to 3.15 times 10 to the 7 seconds. That's a helpful conversion factor. So how many years would that be? Nick, what do I do with my units here?
So 3.
No. I want units first, buddy.
Oh, put year on the top and seconds on the bottom.
Yes. Now you can give you the numbers.
And then 3.15 to times 10 to the 7 on top. And 1. Oh, wait, no.
Yeah, I was going to see how long it took you to realize.
1 on the top and then that on the bottom.
Yeah. So,
I just had to write it down real quick.
all right. Well, someone else can calculate it. We're going slow. Let's go fast.
Would it be 1 times 10 to the 4th power, maybe? I tried to put it in scientific notation, I think.
Why is it bigger than 1 million?
No. So it
Then
doesn't have
let's
to
just
be.
round it to 2 sig figs and leave it as a number.
Okay.
You shouldn't have to overthink this, Olivia. You should be able to just tell me what the number is. Just look at the number and tell me the number. Can anyone else read this number for me? It's just a number. Round it. Read it. The decimal point is there.
1600?
1600 is 1,600. Is that what you meant to say?
Yeah.
No. You meant to say 16,000.
Oh,
Look,
yes.
Nick, this is what people mean when they say 1600. This is what people mean when they say 16,000, right? You believe me, right? Is your number 1600 or 16,000?
I got 1600 on mine.
Well, then you done fucked up, son. All right. So, look, Nick, are you using your, show me your calculator. What are you doing? Okay. Look, EXP, watch me. Ready? 5 EXP 11 divided by 3.17 EXP, sorry, well, backspace, 3.15 EXP7, sorry. That's what I get. The camera's a little blurry, but the decimal point is there. That's 16 with 3 zeros after it, right?
How is mine off by? That's
I-
weird.
That's what I'm trying to figure out. I'm worried that you might have typed times 10 or something. I don't know. So in other words, I thought you misinterpreted 16,000 as 1,600, but you actually got 1,600, right? Okay, these are the confusing things that happen when we communicate with each other. Students, is 16,000 years a reasonable lifetime for the sun? Why not, Adrian?
I don't know. That just seems like a very, very short time. And
Yeah, I mean, like, how old are dinosaurs? 65 million? The dinosaurs were wiped out 65 million years ago.
That's barely enough for any species to even slightly evolve.
Right. Now, the Bible claims, I think, the book that the Earth is 2,000 years old, so it's good enough for that book. But it's not good enough for any other geology textbook, which will clearly demonstrate that the geological sediment layers of Earth are applied down maybe every 100 million years or so. So the sun cannot be a ball of fire. Let's write down the moral of the story. The moral of the story goes like this. The sun is not a ball of fire. It is a nuclear ball, if anything. Okay, that's a cute little problem to demonstrate. By the way, there's a historical reason why you're doing this problem. Do you know who invented the physics necessary to understand nuclear fusion? Nuclear fusion was invented by nature, I suppose, because fusion's been going on for longer than we've been going on. But fusion as a concept wasn't discovered until Albert Einstein poked his head out of the ground and said E equals mc squared, right? So before E equals mc squared, scientists were really stressed out about how old the Earth was, because they knew the sun had been shining for at least as long as the Earth was around. Otherwise, you wouldn't have fossils of plants and things. The sun's been shining for hundreds of millions and even billions of years, and yet it's not a ball of fire. And because they didn't know what fusion was, they couldn't imagine how you could produce an energy source that would last that long, and they were confused. This was a demonstration of why they were confused, because they knew that the sun as a ball of fire could only shine for 10 to 20,000 years. When E equals mc squared came along, they said, aha, now I get it. It's fusion that powers the sun. The next problem will demonstrate that fusion can make the sun shine for a long, long time. And Andrew, I volunteer you to read us number 56. Okay.
It is the lifetime of the sun.
Lifetime of the sun.
The sun's chemical composition was about 70% hydrogen when it formed, and about 13% of this hydrogen was available for eventual fusion in the core. The rest remains in layers of the sun where the temperature is currently too low for fusion.
Okay, Andrew, before you continue, let's all draw a cartoon picture for that. So this ball represents the sun, and roughly 3/4 of it is in the form of helium, and helium is not involved in the fusion reactions. So that cannot be part of the fuel. Only the 70% hydrogen can be part of the fuel of the sun. But fusion doesn't happen everywhere inside the sun. Fusion can only happen here in the very, very high temperature core, which comprises 13% of the mass of the sun. So, in other words, only the hydrogen here, which is hydrogen and not helium, and is hot enough to fuse, can actually contribute to the lifetime of the sun. Okay, Andrew, I'm sorry, I had to interrupt you there, so why don't you keep going?
Oh, I wasn't even muted. Oh, whoops.
Sorry.
Use these data and the sun's mass to calculate the total mass of hydrogen available for fusion over the lifetime of the sun.
Okay, so the mass of the sun is, again, 2 times 10 to the 30 kilograms. In part A, we want to find the mass that can be used for fusion. Basically, we want to find the mass of our gas tank here. Do you guys know how to find the mass of just this red stuff here? How would I do that? Adrian, you seem to be pretty good at percentages.
It would be 13% of the 2 times 10 to the 30 kilograms.
That would give you the mass of all of this ball, Adrian. But almost a quarter of that ball is helium, right? And that won't contribute. So if you just take 13% of the mass of the sun, you get the mass of this entire core. But some of that core is helium. Yeah.
So 70% of the 2 times 10 to the 30, and then 13% of that?
Beautiful. That's exactly. And let's write that symbolically so everyone can see what you did. He took the mass of the sun, multiplies by 70%, which we now know is 0.7. And then once we have the 3/4, then we multiply it by 13%. That's very good. Let's do that together. And Adrian, you can punch it up or anyone else can.
Uh, 1.82 times 10 to the 29th power.
I'm just going to keep 2 sig figs for fun.
All right,
And the units?
kilograms.
Good. And this is the mass available for fusion. Okay, Andrew, read us out part B.
The sun fuses about 600 billion kilograms of hydrogen each second.
Hold on,
Based on
Andrew. How many zeros are in a billion?
9.
Excellent. You've been trained well. And that's kilograms per second, right?
Yes.
That's what we would call the fusion rate of the sun. All right, keep, by the way, that's the mass fusion rate, sorry.
And it says, based on your result from part A, calculate how long the sun's initial supply of hydrogen can last. Give your answer in both seconds and years.
Olivia, you've become a resident dimensional analysis expert now because you handled that second problem so well. How do you think we could jiggle these units around? We've got 1.8 times 10 to the 29 kilograms and 600 billion kilograms per second. And once again, we want to figure out how long. What do you think we should do?
So would it be 1.8 times 10 to the 29th kilograms times 1 second over 600 times 10 to the 9th kilogram?
Damn, see how good you are? Math is never going to confuse you again. That's one way. I'm going to show you an even slicker way to do it. Your way, what you said was beautiful. That's what I wanted you to say. But let me show you an even cheesier way to do it. You just say 1.8 times 10 to the 29 kilograms, and we'll just divide it by 600 billion kilograms per second, and the kilograms will cancel, and then 1/1/2. It's the same thing as what you said, right? I just kind of
Yeah, that's like simplified. That's easy.
yeah. I wanted to show you that that was another way to do what you said. Okay, so let's hear the number and the units.
Okay, I got 3 times 10 to the 17th seconds.
Cool. How many years is that? What's the conversion from years to seconds? I gave it to you in the previous problem.
Yep, it would be 1 year over 3.15 times 10 to the 7th seconds.
When astronomers want to remember that, they remember it as pi times 10 to the 7 seconds. In fact, it's a little bit more than pi, but whatever. Anyways, how many years is that?
Okay, I got a really big number, but I'm assuming we can put it in scientific notation because it's like 9 million or billion.
Is it million or is it why don't we put it, give me 2 sig figs scientific notation, then we'll worry about what it is.
Okay. 9. Well, yeah, 900. No, 9.
9 point something
20.
times 10 to the something is what I want to hear, Olivia.
9.5.
Times 10 to the what?
Nine or 8.
Yeah.
I always get tricked up like on this part.
You don't have to get tricked up. All you have to do is be able to count to 9, okay? The
Yeah.
decimal place is there.
Mhm.
How many times do you have to move it to get between 9 and 5? 1, 2, well,
Yeah, 9.
9.
9.
And that's years. Okay, now we can worry about what that is. What is that in plain English? Andrew knows because he just told me what 9 zeros means a moment ago. Andrew? What's that number? What's that number mean?
It's 9.5 billion years.
That's right. 10 to the 9 is a billion. So in other words, the sun is going to live close to 10 billion years thanks to fusion, which is plenty enough time for the Bible, the dinosaurs, and even more, okay? Actually, I guess it's, all right, I'm going to stop with the Bible thing. You know, I'm not trying to make this political, just trying to have some fun with you all, okay? All right. So 9.5 billion years. Part C, Andrew.
Part C is given that our solar system is now about 4.6 billion years old. When will we need to worry about the sun running out of hydrogen for fusion?
So the sun wasn't born yesterday, if you know what I'm saying. The age of the solar system is 4.6 billion years old. So how much time do we have left with our sun? How do I get that one? I just want to make sure your brains are working this morning.
I mean, we could do this one simple, just based off the answer to the last one, right?
Yeah, this is wicked simple. Is that Nick that I'm talking to?
Yeah.
Nick, it's all right. So keep it simple. What do I do?
We just add, so it'd be 5.4 billion.
Yeah, that's not adding, that's subtracting, right?
Well, yeah, I mean, either or.
All right, you're adding a negative, I guess. I don't know. All right, here. So in other words, Nick just did 9.5 billion years minus 4.6. All right, Nick's with me anyways. Is five, oh, I always have trouble with this. Yeah, 5.4 billion years. We've got 5.4 billion years left to party before the sun burns out. And God knows it's going to burn out before I do. Something to think about philosophical wise. You know, humans didn't even exist more than a few million years ago, right? Like, I guess it depends if you want to talk about humans as Homo sapiens or if you want to get Homo erectus into it or whatever. Homo sapiens. Oh. Homo sapiens as a species have only been around for 1 to 2 million years. And if you want to start getting into the ancestors, Homo ancestor, what's Homo erectus? Still only a few million years. I don't think humans are going to make it to the end of the sun because we couldn't stay humans forever. On long time scales, life evolves and changes and morphs. Start out as humans today, 2 or 3 million years from now, we might turn into hyper intelligent dragonflies or something. You know what I mean? Or more likely cyborgs or something cool like that. But life is dynamic and it's in flux. So I don't think whatever is, if anything is left 5.4 billion years from now, I don't think it's going to resemble anything like, well, maybe the trilobites will still be around. Or what are those things? I saw them at the beach the other day, those horseshoe crabs. Horseshoe crabs might still be here, but I think we're going to look different. And that will be fun. Okay, let's move on to the next problem. We're going to switch it over to chapter 7, number 46. This is a problem that we're going to cover in our class today. It's about density. Do you guys know what the definition of density is? Wait, actually, hold on. I don't know what this problem is. Who's read? Janabelle, have you read from me yet? You did a reading, right? And Olivia did, and Andrew did. Nick, in your loudest reading voice, chapter 746. I think this is the density of a planet problem, right? Okay.
Yeah, I got it. Density classification. Calculate the density of a hypothetical planet in our solar system with a mass of 5.97 to 10 to 25.
Hold on a sec, Nick. Well, You took that
Speaking is difficult.
5.97 times 10 to the 25 kilograms?
Yep.
And the radius?
Radius of 12,800 kilometers. Give your answer in units of grams per cubic centimeter based just on density. Would we consider it largest terrestrial planet or the smallest Jovian planet? Explain.
It's customary to measure densities in grams per cubic centimeter. We're going to have to do a lot of unit conversions here. Let's draw the picture of the planet. The planet has radius r and mass m. I like to use the symbol delta for density. That's just what I do. Does anyone know the definition of density? Hell, the units could probably tell you what the definition of density is. A density is a what divided by a what?
Is that a G? Is it gram divided by centimeter?
Cubed.
Cubed.
That matters, right? A centimeter and a centimeter cubed ain't the same thing. Okay, Olivia, so what's my formula? Since you're so good at units, you can actually tell me the formula just by looking at the units. Grams measure what?
The weight?
Fuck no.
Or the,
Weight is a force.
oh, sorry.
Remember, because of gravity, this has a weight, which is a force, but that's not the same thing as grams. Grams measure
this, no, I don't know. The size? Or the,
definitely not the size.
no.
Mass.
Mass. Thank
Mass?
you.
Oh, okay.
It's a measurement of mass. Cubic centimeters, what are they a measurement of?
The, I don't know, not the distance or, no, I don't know.
Anyone?
Area?
No, area is length times width, right?
Right. Oh, more like volume?
Volume. Volume is cubed. Now, just so happens I took me a geometry class back in the day. And in geometry class, they teach you the volume of a sphere. The volume of any sphere is 4/3 pi r cubed. As Khaleesi would say, it is known, okay? It is known. The volume of a sphere is 4/3 pi r cubed. Now, if I plug that into this volume here, I will get the formula for the density of a planet, which is what we need today. The density of a planet or moon is 3 times the mass over 4 pi r cubed. That's my dude. 3m, you'll notice the 4/3, the 3 flips back up to the top there. Now, my first issue of business is my mass is in kilograms and my radius is in kilometers. But you'll notice those aren't the units that we need for our final answer. So we got to do some dimensional analysis. Janabelle, why don't you help me do kilograms into grams?
Okay.
So we'll start by making a division bar, and then you'll help me put the units into place.
Okay. So put, are we gonna put the 5.97 times 10 to the 25th power?
So there's my mass. I need you to put units top and bottom. What are your current units?
Kilograms.
Okay, what units do I want?
We want volume.
Do you know what this is?
Grams.
Yes.
Okay.
So tell me what units to put here then.
You're gonna put kilograms and then gram at the bottom.
But then I'll have kilograms times kilograms over
Okay.
grams.
I wasn't confused with the first set, and then after that, okay.
But
So-
you want to, whatever's on the top, you want to kill that off, right?
Yeah.
That's actually on the top.
Okay.
So what do I do?
So we flip them. So
Yeah.
kilograms on the bottom, grams on top.
And now you need a conversion from grams to kilograms.
Yeah.
The first day I taught you what a kilo is. Look at the chart for powers of 10. There's a little table of common powers of 10.
I'm looking at it. So
It won't say grams, but it does tell you what a kilo is, and that's all you need to know.
is it 1,000?
Yes. Where's the 1,000 go?
At the bottom.
What goes on the top?
1.
So 1 gram is 1,000 kilograms.
I'm sorry. I know I'm doing this incorrectly. I'm like a little lost right now.
That's okay. I mean, that's kind of part of learning how to do it correctly, is being lost, getting confused, and then figuring it out. So I guess in my experience, this is a kilogram, right? It's like a brick. I don't want it dropped on my head. But a gram is like teensy weensy tiny, right? I should have a whole test mass set here. In other words, Janet Bell, it's
The 1,000 goes.
yes,
1,000 goes on top and the 1 in the bottom.
that's right, because a kilo means 1,000. So 1 kilograms is 1,000 grams. Okay, now add 3 zeros to this number and you're done.
So 1,000 to 24.
No, in other words, this is 5.97 with 25 zeros after it.
Okay.
If you multiply by 1,000, you're going to add 3 more zeros.
Okay.
So what's my power?
27. 28.
Thank you. Grams. All right. Nick, could you help me convert 12,800 kilometers to centimeters? You guys are kind of slow today, so I don't have time for your slowness. Kilometers on the bottom, meters on top, meters on the bottom, centimeters on top. Nick, at least give me the numbers.
1 would go at the kilometer, right?
Yeah? How many meters in a kilometer? It's a kilo. Same thing as before.
Oh, 1,000, yeah.
Okay, what about a centimeter? How many centimeters in a meter?
Is 100 centimeters per 1 meter.
That's correct. Let's do this in our head. I'll move the decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9. And I will get 1.28 times 10 to the 9 centimeters. That's my radius. Now we're going to plug this into our formula, and we're going to calculate our density. The density is 3 times 5.97 times 10 to the 28 grams divided by 4 times pi times 1.28 billion centimeters cubed. Punch them up.
This might be like a stupid question, but so when instead of multiplying like on the denominator, when I'm plugging it into the calculator, I do divide, right? So it knows to keep dividing it.
Correct. Divide by 4, divide by pi, divide by 1.28 exp9 cubed equals.
Oh, cubed. Okay. Okay, hang on. I just forgot to cube it at the end.
Okay.
Would it be 6.8?
Yeah, what are the units?
Oh, would it be grams times, or grams divided by centimeters cubed?
Exactly.
Grams
Grams
over
per cubic centimeter.
grams per cubic centimeter. Okay.
Box that. Now, the final part of this question asks, is this a terrestrial or a Jovian type planet? Do you guys know the difference between a terrestrial and a Jovian planet? That's supposed to be part of our lecture today, but I'm just curious if you know what that is. What is a terrestrial versus a Jovian planet? Well, shit. I guess you're going to learn some stuff. Or do you know, Janabelle?
I'm just thinking a wild guess.
Yeah.
I mean, terrestrial could be planets that are within our galaxy, within our specific galaxy, because I know there's like different galaxies.
Yeah, the galaxy is a bigger thing. All planets, okay, how do I say this? We're just talking about our solar system, Janabelle. We have both terrestrial and Jovian planets within our own solar system. I think I have a picture of the solar system up here somewhere. Some of these planets are terrestrial and some are Jovian. So Janabelle, the galaxy is a bigger order of structure. Yes, there are other planets in our galaxy and in other galaxies, but in our own galaxy, in our own solar system, these are the terrestrial planets, and these are the Jovian planets. Basically, they sometimes call these the rocky planets, because their surfaces are solid. Can't really spell. And they sometimes call these the gas giants because they're big balls of gas. So that's the difference between terrestrial versus Jovian. Terrestrial means like Earth. Jovian means like Jupiter. Okay. Let's look at the fudge. My mouse is acting creepy here. Densities. So here are some common densities. I don't know why they arrange them. Oh, these are in kilograms per cubic meter. What? All right, here we go. Here's the density in grams per cubic centimeter for all of the planets. Our planet is 6.8 grams per cubic centimeter. Would you say it's more like a terrestrial or more like a Jovian?
More like a terrestrial.
Yeah, it's got a higher density, so it's more like a terrestrial. Very, was that Adrian?
Yes.
Okay, cool. Thank you, Adrian. All right. We still have one problem left, but I could use a little break and then we'll start lecture and we'll just work it into our lecture. Does that sound okay to everyone? So that I can get a little pause here to recharge myself? All right. So let's take a 10-minute pause. At 12:11, we will return. Okay? All right. I'll see you guys then. Okay, everyone. I'm back. I indulged a bit. Anyone else there? Okay. So in our last class, we lectured a bit about the sun. And honestly, I'd like to teach you more about the sun, but we're running a bit short on time. I think this is our second to last week, right? Next week is our last week of class. So we're going to want to get ourselves right into the planetary science while we can. So today's lecture is going to be a mixture of Chapter 7 and Chapter 9. Actually, I think the lab that we're going to do today in that case, sorry, let me share my screen with you guys so you can see what I'm up to. I believe the lab that I'm going to want to do today is the Lunar Features Lab. And Lunar Features is Lab 9. So we're actually going to skip Lab 8, the rotation of the sun. Let's all make a note of that. We're skipping Lab 8 and going to Lab 9 tonight. Let's grab our slides showing us an overview of the solar system. We were just looking at it a moment ago. I've got a better slide for that. Sorry, things are, ooh. And our lab on planetary geology. All right. I want to give you guys a sense of what planetary geology is all about. It's a branch of astronomy. Sometimes they refer to it as comparative planetology. Function F5, number 3. Do you guys know what we're looking at here? What is this astronomical object?
The moon.
You'd think so, but it's not,
Okay.
Andrew. It's not the moon. It's a different object. It's actually the planet Mercury. But they look quite similar if you're not trained in the dark arts of planetary science. To a planetary scientist, they could look at small, subtle details and features and recognize this as Mercury and not the moon. Both are cratered rocks in space, but Mercury has these telltale signs. Do you see that little crack right there? That crack is actually a gigantic cliff wall that runs for hundreds of kilometers. It's called a scarp or an escarpment. And it's basically like a giant cliff wall. You'll notice it slices right through that crater there. You can find such walls all over the surface of Mercury. These walls are one of the telltale signs that you're looking at Mercury. And these subtleties are things that you want to learn to identify over time, all right? So let's have an overview of the solar system where we look at all of the planets. Right now we're skipping Pluto and we're skipping the asteroids and the comets. And we're focusing on the planets themselves. We can divide them into two rough, well, actually, the first thing that we might want to talk about is where the solar system comes from. And we learned during our office hours today that the sun is about 4.6 billion years old. And we believe that the entire solar system formed together through a process known as the nebular theory, formerly the nebular hypothesis. It's now been elevated to the status of the nebular theory. I got a couple of different slides for that in another lecture show, but there's one that I like. I like this one. The nebular theory is demonstrated by this image here. It's the idea that our solar system formed all at once from a single collapsing nebula, which was comprised of dirty hydrogen and helium gas. And as the gravity of this cloud contracted, it first flattened and increased its rate of spin. Most of the material fell in towards what would become the sun, but some of the material had too much spin to fall into the sun, and this material eventually condensed down to form the planets. Let's take a note on that. So, the formation of the solar system is explained today by what is known as the nebular theory. And the theory goes something like this. The sun and planets formed 4.6 billion years ago, thank you, from a single collapsing cloud of a single collapsing, let's add a word in here, this is important. Homogeneous cloud of dirty hydrogen and helium gas. Students, What is meant by homogeneous? I always just like to verify that you understand my words.
It's comprised of the same, I don't know how to put it into words, but it means it's all the same.
It's well mixed, right? Like pancake batter. But you're right, it means it's all the same. I like to say well mixed. The cloud was uniformly distributed with little bits of metals and rocks and water, but it was mostly hydrogen and helium gas in a paste, in a fine paste. Now, this leads to some questions, right? And one of the big questions that we have in planetary scientists goes like this. If the planets form at the same time from the same, for lack of a better word, I'm going to put it as batter to continue my pancake analogy. If the planets form at the same time from the same batter, then how do we end up, or how did we end up with these 8 freaks we call the planets? I mean, the idea is that no two planets in our solar system are exactly alike, as this picture here, as this picture here demonstrates. Earth has water and life. Jupiter has swirling stripes of beautiful red and yellow clouds. Saturn is a yellow sphere with massive rings. Uranus is green. Neptune is blue. Mars is red and lost its water. Venus cooked itself as a hothouse. Mercury is a dorky rock near the sun. How do you end up with these unique weirdos, no two of which is exactly alike? And yet somehow these guys, they all came from the same well-mixed homogeneous gas cloud. What do you think? Is there a simple answer to that question? In a way, there is a simple answer to the question. If you really want to know the short answer is physics plus time. And that's kind of at the heart of what planetary science is all about. Ultimately, it's basic forces of nature working over time that create these planets. And we want to start by looking for clues or for similarities. One of the ways, no one had a GoPro 4.6 billion years ago to watch the solar system form. We're just kind of stuck with the pieces of evidence that we have today. Let's play the game. On the left is Mercury, on the right is the moon. They have some things in common and they have some differences. Can you guys tell me without any special training what the differences and similarities are between Mercury and the moon here? And while you explain this to me, I'm going to take a bite of a sausage, egg, and cheese sandwich.
Can you
What do you think?
Sorry, before you eat, can you explain the question again?
Can I repeat? Yeah, okay. The question is, comparative planetology means that you are playing Sherlock Holmes for the planets. What you're trying to do is you're trying to look at the planets and ask, what things do they have in common? and then what things make them different, and then try to answer the question why. And what I wanted you to do, Janabel, is just say, can you look at these two pictures of the moon on the right, Mercury on the left, and can you tell me some things that they have in common? And can you tell me some things that they have not in common or different?
Okay, thank you.
Well, Janabel, do you have an answer?
Yeah, I'm thinking about it right now. I
All
mean,
right.
a pretty obvious part about it is that the moon on the right has darker shading, but I know you explained that earlier.
That's important. That's important. The moon has this stuff, right?
Yes.
This is what is known, that'll be part of our lab today. The moon has two main types of feature. It has what are called the lunar maria. Maria are Latin for seas. And it also has the lunar highlands, kind of like the Scottish Highlands. The highlands are heavily cratered terrain. The maria are the dark, can I, oh, shoot. I guess once I have them there, I can't move them anymore. So this is the maria right there, and these are the highlands. You don't really see maria on Mercury. That's one of Janabel's first observations, and I agree. And there's a reason why, but we have to think about it and study it. That's one of their differences. What do they have in common? Oh, sorry, Janabel. You're muted. Wait.
The
No,
little
you're-
sparkly refraction, like the little sparkly things on the planets.
Are you talking about this stuff?
Yes, those.
Those are impact craters. Those are places where rocks flying through space have smashed into the surface of these worlds. Another commonality you can see is neither one of them has an atmosphere. They are both just rocks floating in space. Now, some other differences, I told you about these things called scarps. Scarps are short for escarpments, and Mercury has them and the moon doesn't. And the scarps are, do you see how that looks like just like a little, it looks like a little scratch. But in actuality, you're looking at this from very, very high up and very far away. If you were to stand in front of those scarps, they would be long cliff walls that stretch all across the surface of Mercury. So in some ways, they look the same superficially. They're both rocks. They're airless. They have no atmosphere. They both show heavily impact crater, evidence of impact cratering. And yet there are some telltale differences that distinguish the two. The moon has these maria, and Mercury has these scarps. Why? What happened to these two weirdos over 5 billion years to turn them into slightly different versions of each other? The first thing that we can do is we can start by sort of classifying planets in one of two broad categories. And I'd like to do that as a set of notes. While not everything fits neatly into this picture, there are two sort of types of planet. There's what's called terrestrial or rocky planets, and we'd like to contrast them with Jovian or gas giant planets. By the way, it's also good to know the names of your planets. Mercury, Venus, Earth, and Mars are the terrestrial planets. Jupiter, Saturn, Uranus, and Neptune are the gas giants. I would have liked to write them out, but it would have taken a while, and I don't have the board space for it. People remember the order of the planets using a mnemonic device. My very educated mother just served us nothing. Okay? So what are some differences? The terrestrial planets are close to the sun, and the Jovian planets are far from the sun. That in itself tells you that there are basic forces that are, you know, if there was just no rhyme or reason to it whatsoever, you'd expect the planets to be higgledy-piggledy scattered around in different orientations. The fact that all of the rocky planets are close to the sun and the gas giants are far from the sun, that's meaningful. That doesn't happen randomly. It tells us that being close to the sun will change the way a planet forms over time. And yes, it's going to have something to do with sunlight and temperature. Most importantly, terrestrials have different compositions than gas giants. Terrestrials are made of rock and metal almost exclusively, whereas Jovian planets are mostly made from hydrogen and helium gas, plus some ices. But mostly it's hydrogen and helium gas. One of the key parameters, it turns out, that allows you to differentiate a terrestrial versus a Jovian is one that we explored today. And that's density. So a key difference between terrestrials and Jovians terrestrials tend to have high densities in the vicinity of 5 grams per cubic centimeter. Jovians tend to have low densities in the vicinity of 1 gram per cubic centimeter. And I'm going to give you a table of common densities in just a few minutes. There are other things too which separate these guys. The terrestrial planets have very few or no moons. This is also a good opportunity for me to figure out what you know about our solar system. How many of the terrestrials do you think have moons? Does anyone know from watching science fiction shows? I love this science fiction show called The Expanse, which is on Amazon Prime. And it's a murder mystery that kind of takes place throughout the entire solar system. And it's cool because they go to all these different planets and moons. And that makes it fun. So I don't know if you guys, you know, maybe watched one of these shows and have a sense, which of the terrestrial planets have moons?
Terrestrial rocky.
I'm sorry?
The terrestrial rocky planet.
Planets. Yeah, which one have moons? If you just consider it Mercury, Venus, Earth, and Mars. I'm sorry, are we talking at cross purposes? My question to you was, which of these planets have moons? Well, I'd sure fucking hope you know that one of them does, right? Otherwise, you just ain't been looking up at night.
Oh, Earth. Okay. Sorry,
Yeah.
I was thinking into it. I was looking at the chart.
Well, what else? Any of these others have moons? I guess y'all don't know.
Would it be Earth and Mars?
That's correct. Mars has 2 small moons named Phobos and Deimos. Neither Venus or Mercury have moons at all. And even still, like, we don't have, Mars's moons are really tiny. Let me show you a picture of Phobos. Oh wait, I'm not sharing my screen with you guys. I thought I was. So this is a picture of Mars's moon Phobos. What does this look like to you guys? It's only about 12 kilometers across, I think. Does that resemble anything? What does that moon resemble for you?
It looks like our moon.
No, it don't.
No.
Well, all right.
Well, it's a little more like bumpier, I guess.
I think you meant because of the craters, right?
Yeah, that's what yeah.
Yes, it does have that, and that's an important fact, Olivia. The fact that this small thing has craters, and the moon has craters, tells us that small things have craters. But the moon is like 3,400 kilometers in diameter, Olivia. It's so big that it's deformed into a round sphere, right? Like our moon is a sphere, and it's way freaking bigger than this thing. This thing's only 12 kilometers across. The first time I saw this, I thought it looked like a blank, fill in the blank. Mm.
It looks like a strawberry to me.
That's very cute. That is very cute. Oh, did someone say something else?
It looks like a golf ball.
Oh, I was thinking of something in space, but I guess
I know, you were asking what does it look like. I don't know. It's like that's what it resembles.
that's totally legit. It's legit. I think what it was, guys, is I grew up just geeking out on science fiction and loving space stuff. So
It just kind of looks like an asteroid that got caught in orbit.
yeah, Nick. Okay, somebody's on my page here. Nick, that's what I wanted to hear. I mean, the first time I saw this, Nick, I thought, this looks like a damned asteroid. And then exactly, Nick, you may already know this, but if you look at the asteroid belt, in our solar system, the asteroid belt is just outside the orbit of Mars, right? So it's not, hold on, I want this picture here. Why does the internet suck? Okay, here we go. Look, Nick, it's not out of the realm of possibility that Mars could have picked one of these things up on its journey around the sun, right? Mars could be orbiting the sun, and one of those asteroids, if it wandered too close to Mars, could be easily captured. So the point that I'm trying to make, Nick, is there's only 2 planets in the terrestrial zone that have moons, and one of them has 2 moons that basically just look like captured asteroids. And that's kind of like, it's a moon, it's a satellite, you know, but it's not a moon, you know, like a moon. Ganymede is a moon. Do you guys know what Ganymede is? Ganymede is the biggest moon in our solar system. It's a moon of Jupiter. I mean, my friends, this is what a GD moon looks like. Ganymede. Now that's a moon. That's a real color picture, believe it or not. It looks like a Jackson Pollock painting. It's crazy. How many of the Jovians have moons?
Don't at least Jupiter and Neptune?
Also Saturn and Uranus. They all have moons. And they don't all just have like a moon. They all have like 60 moons. They have crazy numbers of moons.
Doesn't Jupiter have like 43 on its own?
Jupiter has 63, but the problem is, Adrian, they keep finding new ones every year, some of which are just crappy little asteroids. But do you know that last year they discovered 10 new moons of Saturn, and now Saturn has more moons than Jupiter officially? 79 moons on Jupiter. And Saturn, I have to look it up because it literally changes every year. 82 moons. They discovered 20 of them like a year ago. Isn't that crazy? That's a crazy number of moons. So, and Uranus and Neptune have slightly less, but they have like 20 to 30 or so. Maybe they have dozens of moons anyways. All 4 have many moons. There are no rings around the terrestrial planets. And I'll just save you guys some time. It turns out that all 4 gas giants have rings. And the list honestly goes on. There's more and more things that separate these things from each other. You know, something funny about Pluto is Pluto doesn't really fit into either one of these categories. Pluto is a weirdo in a few reasons. Okay, it's far from the sun, but it has a sort of, let's call it a hard surface, like a terrestrial planet. But the surface is not made of rock and metal, it's made of ice and rock. It also has 5 moons. I mean, the list goes on. Oh, the density? The density is around 2 grams per cubic centimeter, which is too high for a Jovian and too low for a terrestrial. Oh, sorry, this is Pluto. And that makes Pluto and Eris and the other dwarf planets kind of freaky. It doesn't really fit into either category. I'd like to erase when you guys are ready. Nick, are you good? Yep. Are you good now? Okay. All right. So now you have the setup, you know, like this, if this was a game of Clue, you know that there was a murder and you know that there's a mystery to be solved. And now you got to try to look through everyone's cards to figure out what's going on. And these are some of the facts that we have to work with. Let's talk about why density is such an important characteristic of planets. Density tells you a lot about a planet because density is a tracer for chemical composition. And what I mean by that is each atom or each element in the periodic table has a unique density. So you can literally tell the chemical composition of a thing just by measuring its density. One of the best periodic tables that you can use is the so-called periodic table of the elements, the Sergeant Welsh one. This is the one that I used when I was a chemistry student in high school, and it's very, very good. Let's get a high-res image of it. I'm going to want to refer to this a bunch of different times. That's 3,000 pixels. That should do us. Thank you, Ajax, for hire. Why this is such a good periodic table is it's just chock-a-block full of info. Let's look at our legend here. You guys will see that in addition to the atomic number and the average atomic mass, they even give you the electron configuration, the melting and boiling points, crazy stuff. And here in blue, you can see the density as measured at 300 Kelvin. You'll notice that zinc, a common metal, has a density of around 7 grams per cubic centimeter. Notice that each atom in the periodic table has its own unique density, and almost no two are alike. Titanium is different than scandium. Calcium is different than potassium. They all have a unique density. So measuring the density of a substance is one of the simplest ways to just answer the question, what is this thing made out of, okay? Density, of course, is mass divided by volume. And typically, we measure it in units of grams per cubic centimeter. Now, sometimes you'll see people do MKS units of kilograms per cubic meter, but that turns out to not be the best unit to work with. And that's because a cubic meter is quite large. Like, this is a square meter. And a cubic meter, I can barely even put in front of this chalkboard without bumping into the computer. If you were trying to measure the mass of a cubic meter of lead, you would not be able to pick it up off your workbench. On the other hand, a cubic centimeter, well, here's some poker chips here. Wait, I thought I had some dice. A standard dice is about a cubic centimeter. This is not a, actually, this is like a mini dice. I have a little mini dice. So not a standard dice, but a mini dice. This dice is about a cubic centimeter. It's a centimeter on all sides. So, I don't know, that's like the size of a sugar cube if you think about it, right? Or maybe a chicken bouillon cube. A sugar cube is about the size of a cubic centimeter. That's a good sample of material to work with. Even if this is lead, I could probably pick that up. The density of a sphere I know we did this in our office hours today, but I thought I'd include it. 3 times the mass of a planet over 4 pi r cubed. Let's find the density of Earth as a sample problem. Earth has a mass of 6 times 10 to the 24 kilograms. I'm going to give you the quick version here, or 6 times 10 to the 20, let's see, 5, 6, 7 grams. Earth has a radius of 6,400 kilometers. I'm going to give you guys a quick tip here. There are approximately 10 to the power 5 centimeters per kilometer. That's a very, very helpful conversion factor to know. 6.4 times 10 to the 5, 6, 7, 8 centimeters. So to find the density of Earth, I would do 3 times 6 times 10 to the 27 grams over 4 pi times 6.4 times 10 to the 8 centimeters cubed. Could you guys be a peach and punch that up for me? What do you think?
I don't know if this is correct.
Janabel, let me zoom in on you. You forgot to divide at the bottom, Janabel.
Okay, I was confused multiplying and dividing.
Yeah, you want to just divide by 4, divide by pi, and divide by that cubed. Can you guys see my mouse right now? No? Okay. Anyone else get something different? Oh, hey, Ernest. What'd you get?
Can you see it?
Hold on, wait. Let me zoom in on you. You're a little too close. You got to back it up. Your screen is too dark. I think you have to hit second function up to make the screen brighter.
Okay.
Can you read it to me?
Yeah. It's just 3.705.
Is there a power?
Oh, times 10 to the 54.
Oh, 54 zeros. Don't want to forget about that. Hey, you made the same mistake that Janabel did. Ernest, you hit divide by 4 times pi times this, but you have to do divide by pi, divide by that cubed.
Oh, okay. Okay.
Because otherwise the calculator runs into order of operations issues.
Okay.
0.5.
Andrew, yours is too big too. I'm sorry. Who said something just now?
Jamarcy.
Yimmersy, what'd you get?
5.5.
Thank you, Yimmersy. Yimmersy, you speak the truth. I'm gonna have to show everyone how to do that, okay? It's 5.5. What are the units? Yimmersy.
It would be centimeter cubed.
Centimeter cubed are on the bottom. Yimmersy?
It'll be grams over centimeter cubed.
That's correct. The Earth has a density of 5.5 grams per cubic centimeter. But what's it mean? That's not obvious to you guys just yet, because you need to learn about what some common densities are. Let me tell you what it means. Wait, how do I have both me and... Okay. Let me tell you what that means. I'm going to help you guys make a table of common densities. And the table that we're going to make has to do with the 4 ingredients of a planet. So there are 4 ingredients that make up a planet. And we want to know their densities. You can build a planet out of basically one of 4 things. The first is hydrogen and helium gas. The second is water, or what are called hydrogen ices. You could basically say ices there. The third is rock, and the fourth is metal. And each of these things has its own kind of density. The density of hydrogen and helium gas is really low. Maybe like 0.1 grams per cubic centimeter. By definition, water has a density of 1 gram per cubic centimeter. Rock is around 3 grams per cubic centimeter. And metal, is 7 grams per cubic centimeter. So I asked the class, with my pointer stick, what's it mean? What does this mean if you compare it to all this? How does the density of Earth fit into this?
In between rock and metal.
And that must mean it's a mixture of rock and metal. Earth is a mix of rock and metal. That is how we use density when we study a planet. What do you think could you guys guess the density of Pluto based on our previous lecture note? Can you guess, Adrian, the density of Pluto?
Well, it would be between rock and ice, so like 2 grams per centimeter cubed.
Yeah, and that's exactly what it is. If you look up the density of Pluto, sorry, am I zoomed in here? Check out the density, Adrian. 1.854 grams per cubic centimeter. Just like that. Okay. Density is a key indicator of planetary composition. And at some point, you guys probably learned a little bit about the interior of Earth. I know that I had to take a earth science class when I was in junior high school, right? And what did you guys learn about the interior of Earth? Did you have to do that? I'm old now, so hell, they probably taught me about horses and buggies for all we know. What did they teach you? Earth science? What did they teach you about the interior of Earth? What are the layers of Earth?
They taught us mostly the layers of Earth. I can't remember all 4, but I remember
I learned 3.
we had like an interior core and an exterior core, and like the crust.
And what's the last one?
I don't remember that one.
That's
Is it the
cool. They
mantle?
taught you. Oh, sorry.
Is it the mantle or
Thank you, Ernest. That's right.
Okay.
The mantle. Now,
Okay.
I just learned crust, mantle, core, but it is true, Adrian, that the core can be subdivided into an inner and an outer core, and I'm going to make a big deal about that too. So Ernest and Adrian have both heard some of these terms before, but here's a funny thought: the radius of Earth is 6,400 kilometers. what do you think the deepest human beings have ever gone into Earth is? Like, for instance, let me tell you a joke to start this off. There's a book by Jules Verne called Journey to the Center of the Earth. I think they even made a movie out of it. Now, in this ridiculous movie and in this ridiculous book, these intrepid explorers travel to the center of the Earth where they find, I kid you not, dinosaurs. So in this movie, they find dinosaurs at the center of the Earth. Hell yeah. That probably makes for some good, actually, that probably makes for some very bad TV. Okay. Have we gone to the center of Earth for realsies? No. What do you think the deepest place we've ever been to is?
We probably never broke through the crust.
You're correct, Adrian. Adrian, do you have any idea how thick the crust is? There's no reason you should, but.
I forget, but I know it's extremely thin.
It's thin in comparison to the radius of Earth. But remember that radius of Earth is pretty extreme, being 6,400 kilometers. Let me show you my slide that I'm going to show you in just a few minutes. It turns out there's a couple of different ways to layer the interior of Earth. My mouse has disappeared for some reason. Oops, that's because I'm on the wrong slideshow. Okay. Whoa, that one needs to be exited from as well. Sorry, everything's acting kind of funky here. This is how I learned the layers of Earth. I learned that there were 3 layers. Okay, I've learned more since then. But when I was when I was freshman in college or something, I had learned in high school that there was a crust and a mantle and a core. Today, I'm going to teach you that there are 2 different ways that we can think about layering the Earth. Adrian, you kind of gave me a mix of the 2, which was very interesting. But this picture is cool because it shows you that the crust can vary anywhere from 8 to 75 kilometers. Let's just say 100 kilometers to keep things simple in our brains. But I guess, Adrian, is it obvious to you why the crust would vary in thickness? Where would it be thickest and where would it be thinnest?
It would be thickest on like I can't speak. On like higher structures maybe.
Like, where would it be the absolute thickest on Earth? What's the highest structure you can think of?
A mountain.
Like Mount Everest, right?
Yeah.
Where do you suppose the crust gets thinner?
More low areas like craters, valleys, things like that.
Even the seafloor bed, maybe, right?
Yeah.
Like, there are some parts of the seafloor bed, like the Mid-Atlantic Ridge, where basically the crust almost disappears to nothing. It's not quite nothing, but in the middle of the Atlantic Ocean, there's this place called the Mid-Atlantic Ridge, and basically under magma from the mantle actually can penetrate through the crust, and it forms new seafloor crust. So that's probably, so like you said, mountains would be the crust is thickest, and that's where it's thinnest. Now, I'm going to tell you guys, I'm guessing nobody knew this beforehand, but the deepest man-made structure ever created on Earth was done in Russia as a science experiment, and it's known as the Kola Super Deep Borehole. Let's check out the wiki page on that for kicks real quick. So this is the deepest that we've ever penetrated. Hold on a sec. Kola Super Deep Borehole. The Kola, oh, by the way, hold on. I want to change my video settings here. Okay. This is a picture of the Kola Super Deep Borehole. It's a research base in Russia that has since been deactivated. So it's no longer an active science research station, but it now exists as a sort of junkyard or a steel scrapyard. This thing was a pipe. It's now been welded shut and it was just a tiny little pipe. But I believe they drilled, this is a commemorative stamp. In the 80s, they drilled down to a depth of like 12 kilometers. This is what it looks like today. It's basically just a junkyard. And there's the Kola super deep borehole itself. It's been welded shut. It's just this gnarly, rusty pipe. So cool. Now let's think about what 12 kilometers means in terms of digging into the earth. The thing I'm trying to get you guys to understand, what's the deepest man-made hole on Earth? Answer: the Kola super deep borehole. It has a depth of roughly 12 kilometers. The radius of Earth, 6,400 kilometers. What is that as a percentage of Earth's radius? It's 12 parts out of 6,400 parts. Punch it into your calculators and tell me what percentage it is. How would you say that as a percentage? This is also a test of sorts. Well, one significant figure.
It's like 0.
Sorry, no, Adrian, that's not how we play, okay? Adrian, you're never allowed to round to 0. Let's start by looking at the decimal of what you got, okay? I got 2 times 10 to the minus 3, right? Which is the same as 0.002. You are not allowed to round that to 0. That's one significant figure, okay? What's that as a percentage, Adrian?
Oh.
You can do it.
0.002%.
No.
Right.
What is this as a percentage?
%50.
So you know to move the decimal place twice then, right? So try again. What's that as a percent? Did I lose you?
Like 0.2% then?
Yes. You can say it 0.2%. You can also say it as 0.2%. That's the percentage of Earth's interior that that humans have explored. So you know what my next question is, right? What's my next question?
How can we solve the rest of,
Yeah, like,
find the rest of what we haven't touched?
yeah, like how do we know what the heck is in there? Like I'm telling you that the Earth is made of 3 layers, crust, mantle, and core, but I'm also telling you simultaneously that we've only gone down less than 1% into the radius of Earth. How could I possibly know what's in there if I haven't been there? I don't expect you to know the answer to that question, but I want you to think about it. The answer, my friends, are earthquakes and seismic waves. Every time an earthquake goes off on Earth, it makes two types of vibrations in the rock. And they're kind of like the two different types of waves that we find in physics. There are S waves, or transverse waves. That's where the displacement of the wave is side to side, but the wave moves forward. There are also things called P waves, or longitudinal waves. That's where you have a compression followed by a rarefication. Air is an example of a compressional wave. You bunch up and make the air more dense in one region, and the air is less dense in another region, and it travels through space. Slinkies are cool because slinkies can make both types of waves. I don't know if I'd be able to demonstrate it well here. Anyways, let's not get sidetracked. Every time an earthquake goes off, it emits S waves and P waves. Here the S waves are shown as little wiggles. That's the secondary or shear waves. And here are the primary or pressure waves. Now, a good fraction of the Earth, its mantle, is solid. And solid rock will allow both S waves and P waves to propagate. But because we know that the Earth is made up of rock and metal, we know that the metal at the center should be warm and potentially liquid. Liquids allow pressure waves, but they block the S waves. So geologists set up seismograph stations to measure vibrations in rock all over the Earth. When an earthquake goes off, they capture the ratio of S waves to P waves, and they share all the data with each other, and that tells them how big the inner liquid metal core is. This is how we end up with basically a three-part model based on density. It turns out, however, that there are two ways to layer the Earth. It's different if you look at it by density than if you look at it by strength. And that's my next set of notes. Let's do that. So whereas in junior high you learned one method of layering the Earth, density, today I'll teach you two ways to layer the Earth. The first is by density. As you've already seen, density is a measure of chemical composition. But the second measure is going to be by strength, what might also be called rigidity, or you might call it plasticity. Is it strong? Is it brittle? Does it flow? Does it bend? If we layer Earth by density, we get the classic crust, mantle, and core. And this reflects the idea that the Earth is basically made of two things, rock and metal. Hey, by the way, I got a question for the class. Just, yeah, you know, what's a rock? You think to yourself, I know what a fucking rock is. I've seen a rock before, right? Here's a rock, okay? What's a rock? Do you know that even a rock has a technical definition? Does anyone know the definition of a rock? Has anyone taken a geology course with my colleagues Paul White or Emily Burns or Roger Hart? What the hell is a rock? An educated person should know what a rock is.
Is it like part of Earth's crust or Earth's crater?
Well, that's
Does
not
it travel
wrong.
from, like the center of the Earth? Like,
The center of the Earth is metal. The outer layers of the Earth are rock. And by the way, this is an example of granite. It's polished granite on one side, but this is raw granite. These little black flecks here are called feldspar, I believe. I actually kind of suck at geology, I'm not gonna lie. All right, but when I'm in the astronomy zone, I'm comfortable. When I'm in geology, I get kind of bad. But I know some things. I know what the hell a damn rock is. Do you?
Just a bunch of minerals.
Yes, Nick, very good. That's the very definition of a rock. A rock is an aggregate of minerals. And to help add some juice to what Nick said there, here's an example of a slab of granites like the type that I see here, that I just showed you. And you can see a slab of granite, you can actually see some of the mineral structure in it. You can see the white stuff and the black feldspar, and sometimes there's little bits of gneiss and other things. But not all granite is the same, as some of my colleagues know. My colleague Emily Burns, she does this beautiful building tour of downtown Providence. And it's really cool because I walk past these buildings every day since I live down here, and I never really thought too much about it. But she would take me up to these bank buildings and stare at the granite and say, "Do you see this, Brendan? This is granite that comes from Indiana, and this was formed in the Triassic period 60 million years ago. And this is a very special type of granite because of these minerals that you see in here." And it was kind of cool to watch her get excited about rocks. It made me realize that there was a secret world of rocks all around me that I wasn't paying attention to. Now, here's a slab of a particular type of granite. Maybe this comes from New Hampshire, I don't know. And here you can see all the different minerals. And this is what Nick is saying. What a rock is, minerals are kind of like chemical repeating units. Like here's silicon dioxide. Here's dialuminum trioxide, potassium oxide, sodium oxides, calcium oxides, iron oxides. It looks to me like rocks are mostly silicon and oxygen, but then they have a few metals in them as well. In fact, here's some other minerals that might make up rocks. Sometimes they're quite complex. Other times, in the case of carbon, they're just, in the case of diamond, they're pure carbon. I like to imagine what would happen if I had a spaceship like in the Hitchhiker's Guide to the Galaxy that could just vaporize the Earth into atoms. Suppose you just vaporized the entire crust into atoms. This is what it would look like. 50% of the Earth's crust is in the form of oxygen, and 30% is in the form of silicon. So, Nick, yes, it's an aggregate of minerals, but the most common mineral by far, or the common two, are silicon dioxide, which you see in granite, and silicon tetraoxide, which I believe is in quartz. And taken together, these minerals are sometimes just referred to as astronomers as silicates. From now on, when you hear me say silicates, that is top secret code for rocks. So silicate is either a silicon with 4 oxygens or a silicon with 2 oxygens. And there are other variations, but let's pretend like we don't know about any of those. Like I believe, like quartz. Look at the quartz is basically pure silicon dioxide, okay? And granite has some of the, an oxide mineral. Here you can see silicon tetraoxide, and here you can see silicon dioxide. That's basically what all rock is made out of, plus some other stuff, okay? In other words, the crust is made of low-density silicates. The mantle is made of a medium density mixture of silicates with higher concentrations of metals, and the core is high density, and it's basically made of metals. The two metals that the interior of a planet is usually made out of is a mixture of iron and nickel. Iron and nickel are the two most abundant metals. Sometimes people just say iron. Iron is quite dense. I have a meteorite chunk here. I think I showed this to you the other day. It's too bad I can't pass this around for show and tell. That's one of the nice things about class. This damn chunk here it's a lot heavier than you'd think. Here's a letter scale. That's 2 pounds. Granite? 1.5. Or maybe that's 1.25. Actually, no, that's not even 1 pound. That's less than a pound. See that? If you hold granite and metal up side by side, it's clear that this is much denser. So much for what we learned in junior high school. But let's face it. Anytime someone talks about the crust of Earth, you know what people usually tend to think about? They tend to think about that other crust that they like so much, pie crust. And if you're imagining the crust of Earth and you're thinking about pie crust, you're actually not thinking about the crust at all. Come on. Can I get a zoom in on pie crust? When you think of pie crust, you think of the cool, crispy, frozen outer layer of a warm, gooey pie. That is not what the crust is. That is a different way of thinking about the Earth. That's layering the Earth by strength or frozenness. And when you do this, you're actually thinking of something that we call the lithosphere. The lithosphere is a way of considering the outer exterior of Earth as a cold, frozen sort of pie crust that is brittle and is capable of being fractured. Introducing your new vocabulary of the day for layering the Earth by strength. It's called the lithosphere. This is your $10 word. Lithosphere is the cold, frozen, brittle outer layer of a planet. It's important that it forms cracks and it can fracture. Well, not all lithospheres do that, but Earth's does that. The lithosphere floats on top of a layer of rock that is convective, called the asthenosphere. And this is a layer of warm, convective rock. It's basically rock that floats. At this point, probably worthwhile to address a misconception that oftentimes comes about when we discussed the asthenosphere. Especially since they color it red, I used to think that this layer here of the asthenosphere was kind of like a pool of lava underneath the rock layer of Earth. But lava is technically in the liquid state. The asthenosphere is solid, or at best plastic. And the book asks you to consider the asthenosphere to be a little bit more like silly putty. If you had to classify silly putty as solid, liquid, or gas, what would you give it? Adrian says solid, and I'd agree. I guess technically speaking, it's kind of like a plastic. It can deform. So normally the definitions are a solid maintains its volume and shape, a liquid maintains its volume but not its shape, and a gas maintains neither volume nor shape. But silly putty over time will sort of form the egg shape of its container, right? And the problem is this rock, the asthenosphere, is under tremendous pressure and does not exist in a liquid state. It's a solid that is capable of flowing over long time scales. Underneath it is a more solid layer called the mesosphere. And then Adrian, here's the differentiation. The outer core is liquid and the inner core is solid, okay? Let's get all that down. Warm rock. A liquid outer core. And a solid inner core. This is your key concept of the day. The lithosphere is going to turn out to be a measure of, well, the lithosphere has either a thickness or a thinness. And that determines a lot about the interior of a planet and what kind of geology it's going to have. Let me collect my thoughts here. So, the lithosphere is a key measure of the internal heat of a planet. I'm just trying to think of where I want to go from there. Maybe showing you the other, a model of the other planets. No, I wanted to ask a question. I'm sorry. I started to lose it for a second because I wanted to ask you guys a question. Hey, Adrian, I'm just picking on you because I can see your face, okay? What do you think is, and also you're the one who told me earlier about the inner versus the outer core, right? What do you think is warmer, the outer liquid core or the inner solid core?
I feel like this is a trick question and it's going to be the inner core.
That's correct. You are right. I, of course, would ask a trick question. Or you feel like it's not going to be obvious. Now, but let's just review your logic. Why would it seem at first blush that the liquid core might be hotter than the outer core?
Because usually we think of melting points, which are warmer than normal solid states.
I completely agree with you. But the one thing about that is those melting points, Adrian, are all measured under the same pressure conditions, which is 1 atmosphere of pressure, 100, well, 1 bar, 100,000 pascals, or 14.7 pounds per square inch. But the thing is, Adrian, whether you're a solid or a liquid or a gas, it actually depends also on pressure and not just on liquid. And I think one nice way for us to start to learn about that is for us to look at what's called a phase diagram for water. So let me just show you a phase diagram. A phase diagram shows you the melting and freezing points of water, but it also shows you how pressure affects it. okay? And there's a really nice one here. Sorry, my coffee's starting to wear off. We're gonna need tea break soon, I know that. Oh yeah, we're 5 minutes past tea break. But let me just finish my point, if you guys don't mind. This is a wicked cool graph. This graph can actually teach you a lot about stuff. So it shows you, let's look up here. The temperature is on the x-axis, right? But here is pressure on the y-axis. Now, friends, most of you have lived your entire life right here at 1 atmosphere of pressure or 100 kilopascals. And sure enough, Adrian, if you're at 100 pascals, then 0 degrees Celsius is where water will freeze. 100 degrees Celsius is where water will boil, right? But in the interior of core of Earth, pressures can be thousands, if not hundreds of thousands times greater. And at that point, if your pressure goes up by a factor of 100 to 1,000, there comes a point where you just can't have any liquids at all because the pressure forces the water molecules back into ice. Weirdly speaking, Adrian, even if ice was located at the core of Earth, if water was located at the core of Earth, it would be forced into ice crystals. Except they would be wicked effing hot ice crystals. They would be over here somewhere, right? Let's take a different approach. What if you go to the surface of Mars? People remark often that Mars has no water. And that's not entirely true because the ice caps of Mars are full of frozen water and carbon dioxide. But the reason you can't have liquid water at the surface of Mars, because the pressure of Mars is less than 1/100th of the pressure of Earth's atmospheric pressure. So Mars is typically thought of as being much, much colder than Earth because it's farther from the sun. But Adrian, if you took a cup of water to Mars and you opened the lid and held it up to the Martian atmosphere, the water would boil at negative 100 degrees Celsius. And that's because, okay, well, maybe it's not quite maybe it might be 55 degrees Celsius or something like negative 50 degrees Celsius. But most water on Mars would actually boil or freeze because the pressure is not sufficient to form liquid. So if you're on Mars, I bet if you opened up a cup of water, depending on what hemisphere you're in and what time of year it was, probably some of it would freeze into ice and the rest of it would boil away into steam, which would probably look pretty weird to your eyes, right? That would be something you're not used to seeing on Earth. I hope I've made my point, which is just because something's solid doesn't mean it's colder, right? Obviously, the pressure is so great on the rock inside the interior of Earth that the high temperatures are not enough to combat the intense pressure of all this rock sitting on top of you, and it forces it back into a solid lump. Okay. Why don't we pause there? I'm thinking we could all use another break. Yeah? Okay. When we come back, we'll learn about why some planets are warm in the inside and some aren't. And I'll see you guys at 10 past 2. Okay, everyone, we're back after that indulgent tea break there. So if you're still out there, non-video participants, today's lab, we're going to do the Lunar Features Lab. We're going to be sort of getting to know some of the craters of the moon and some of its surface features. A very chill and fun lab. I'm going to hit print on my worksheet now so that it's ready for when we're ready to go here. Let's see. I know you guys sometimes take a couple of minutes to print things out, so you're actually going to need a couple of things for the Lunar Features Lab. I've scanned a high-resolution image of the moon map, and this you can just kind of leave on your computer or iPad so that you can kind of follow along with me. The one thing you will need to print out or at least handwrite a copy of if you don't have a printer is this sheet here, which is the lunar features data sheet. So I'm going to hit print on mine. It should just be a single page. Boom. And you guys can either print or draw that out, but then have your moon maps handy. There are 2 pages. I had to scan them separately. So these are the 2 pages of the moon maps here, okay? And we won't need that until a little bit from now, but I thought you guys might want to get started on that. All right. Are the rest of you guys out there too? I see Adrian, Andrew, anyone else in the house? Olivia, you with us? Nick? Okay. Awesome. Good, because if you don't interact with me, I'm going to give you the pre-recorded lecture. I get lonely up here, you know? I need some friends. Okay. So we just learned that there are 2 ways to layer the Earth, one by density and one by strength. And you guys learned a new vocabulary word called the lithosphere, which is the cold, frozen, brittle outer layer of the planet. All the terrestrial planets have lithospheres. And what we're going to do now is we're going to take a look at a hybrid model showing you the 2 different types of layering superimposed on each other while we look at the 5 terrestrial planets. Now, for this section, which you might be thinking of as a planetary geology section, we're going to consider not only the 4 terrestrial worlds, but we're also going to use the moon as a comparison point. Here you can see the 4 terrestrial planets: Mercury, Venus, Earth, Mars. And the moon, if you think about it, although it's not an official planet, is a quite large astronomical object. Compared to Phobos and Deimos, the moon, Earth's moon, is as large as one of the moons of Jupiter. In fact, it's so unwieldy large for our inner solar system that it's helped the authors of your textbook develop a theory about the moon's formation called the Big Whack hypothesis, where the moon is thought to have formed when a Mars-sized planetesimal crashed into the outer layers of Earth and basically tore a piece of Earth's crust right off of the planet. So because we're hungry for data points, because we only have 4, the moon is another terrestrial-like object that we can consider in our study of planetary science. So I'm going to lay out for you the interiors of the 4 terrestrial planets, and I'm going to include the moon as a 5th data point. And I want you guys to take a look at what happens here. At first, you see a layering of the planets that's done by density. You can see the crust on the outside, the mantle on the inside, and the metal core at the very center. And if you just do a sort of layering by density, all of the terrestrial planets look the same. You see Earth, Venus are completely identical. The moon is missing a little bit of metal in its core, and Mercury has a little bit of extra metal, but for the most part, they're all a mixture of rock and metal, with rock on the outside and metal on the inside. And this is what planetary scientists call the differentiated layering of a planet. The fact that it resembles a kind of Tootsie Roll or a candy with metal on the inside and rock on the outside. However, a different story emerges if you superimpose over that the lithospheres of the planets, which are seen here as a dashed black line. You'll notice that with planets such as Earth and Venus, the lithosphere is quite thin, meaning the part of the planet that is cold and frozen is also quite thin. But check out what's happening here with Mars and with the moon, and to some extent with Mercury. The lithosphere of Mars extends halfway through the planet's radius. And the message that this has to tell us is that Mars's interior is practically frozen solid. This planet has lost much of its internal heat. Why should you give a shit about that? Because internal heat is what drives the interesting, cool geological features on a planet. Things like giant mountains on Mars or those scarps that you see on Mercury. If you're interested in the features on a planet, you have to take some time to consider what caused those features, which is the internal heat of the planet. Why don't we go ahead and take some notes here so that we can kind of codify what I've been talking about. Okay. So there are two types of planetary heat. And we're taking this as a note because they can oftentimes get confused. There is the so-called surface temperature of a planet. And the surface temperature of a planet is mostly caused by the amount of solar radiation that it gets. So the surface temperature is affected by basically three things. It's affected by your distance from the sun, first and foremost. Obviously, the closer you are to the sun, the more solar radiation you get. It's also affected by something called the albedo. The albedo is your percent reflectivity. A planet made of fresh ice will reflect more sunlight than a planet made of dark volcanic rock. So planets have variations in their albedo, which can affect how much radiation they receive or how much radiation they absorb. That's your percent reflectivity. And the last thing, of course, that we're going to explore in our next lecture is the effect that atmospheres play in heating up a planet's surface. So not only Venus, but also Earth and to a small extent Mars have changes in their surface temperature due to atmospheres and the greenhouse effect. But let's say we put the greenhouse effect stuff on pause until next week. Mostly your surface temperature is affected by your distance from the sun. Actually, wait, do you guys, what's the hottest planet in our solar system? Who knows the answer to this question? You want to guess? Adrian, what do you think the hottest planet in the solar system is?
I don't know. The best guess I have for you is Mars, but if it's the closest to the sun, it's probably Mercury.
Mercury is the second hottest planet in our solar system. And although it is the closest to the sun, it's not the hottest. Mars, unfortunately, is a bit colder. Mars is a bit farther from Earth, so it's colder than Earth.
Is it Venus?
Yeah. Andrew, Venus is so stupid hot. Its daytime temperature is like 480 degrees Celsius. That's hot enough to melt lead at the surface of the planet. In fact, so nasty is the surface of Venus that unlike Mars, which we have multiple rovers exploring on, we've only successful, and when I say we, I mean the Russians. We didn't actually do a very good job, but the Russians managed once to land a spacecraft on the surface of Venus. Do you want to see a picture of what that looks like? We got two photos from the surface before the spacecraft melted and succumbed to the temperatures and the acid rain. So let me just start by showing you a picture of Venus from the outside, because you guys might not have seen that before. So let's just bop over. I have a couple of photos in my slideshow, but this might actually be quicker. This is a picture of Venus in natural color as seen from the outside. That yellowish cloud layer that you see is just thick blankets of carbon dioxide. So the atmosphere of Venus is of a different composition than our own nitrogen-oxygen atmosphere. This is just straight up carbon dioxide. And it's thick. It's hundreds and hundreds of times more massive than Earth's atmosphere. Actually, pause for a sec, guys. Sorry, folks, we had some washing machine troubles and, oh wait, I'm muted here. Oh, no, I'm not muted. Okay. We had washing machine troubles, and the good folks here were helping us out. Anyways, this is what Venus looks like if you fly outside of it in your spacecraft. We've mapped the surface of Venus, even though we can't see it that well, by bouncing radio waves off the surface and learning where the mountains are. I'm hoping that you might actually be able to see the two. I have the photos in my slideshow. I was assuming they would have them here in the Wikipedia page. If not, they've really done a disservice. Wow, this Wikipedia page is epic. That's crazy that they wouldn't. Let me show you guys, because I have it later on in this slideshow. This is the spacecraft that the Russians actually managed to get to the surface of Venus. It was known as the Venera 12 and 13 missions. And here it is looking all cool and 80s-like in the clean room there, probably in some Soviet university technical room. The spacecraft was designed to fly to the cloud tops of Venus and drop a probe down by parachute to the surface. They knew it wouldn't last long before it was overheated and destroyed. This is the first photo that they got back from the spacecraft. Now, do you see that little thing right there landing on the ground? That's the lens cap of the camera that popped off just a few seconds ago, and you can see it dissolving and melting in the caustic acid rain atmosphere of Venus. And can you see here, this is the lander of the spacecraft? Notice how the metal is slowly dissolving and being eaten away by acid rain clouds in Venus. Now, if you poke over here and you check out the ground, you can see nothing but slabs of volcanic rock. And because they look sharp and jagged, you can see that there's actually very little erosion on Venus. There's no water and there's no wind. Even though it has a really thick atmosphere, the planet doesn't rotate. So there's no wind on Venus. So that means there's almost no erosion. One of the reconstructions of the second photograph looks like this. Venus is probably the nastiest planet in the entire solar system. It's just slabs of volcanic rock and mountains and nothing else. Anyways, those were the only two pictures that we got from Venus. Not fun. Okay, I just went on a huge tangent, but the point was to tell you that surface temperature is mostly affected by distance, but the atmosphere does play a role. Today, we don't want to focus so much on this type of planetary heat. We want to focus on the other type of planetary heat, and that's the internal heat of a planet. The internal heat of a planet is important to us because the internal heat is what determines the amount of cool geology a planet has. The geology is affected a little bit by surface temperature, but a lot of the geology is affected by the internal heat of the planet. The internal heat of a planet is caused by three factors, and the book spells them out for you somewhere around slide 20-ish or 30-ish. There we go. The first is something called accretion. And that's just the formation of the planet when its gravity coalesces to form this rock. The second is differentiation, where the heavy metals sink down and the lighter materials rise. And the third is actually radioactive decay. And I'm going to talk a little bit about each of these. So the internal heat is affected by three factors. One, accretion. To accrete something means to stick to. So for instance, if you ever built a snowman by taking a small snowball and rolling it along the ground, and then you watch it turn into a bigger snowball, that little snowball is accreting snow. So accretion is basically the heat of formation. That heat of formation is ultimately coming from gravity. from gravitational potential energy. In fact, students, 4.6 billion years ago, if you could have flown through our solar system and had a little GoPro out to record it, shoot, you probably would have seen something that looks like this. This is probably what the Earth would have looked like shortly after its formation here. I'm willing to bet that the forces involved in dropping all of those bits of rock and squishing them and compressing them down into a sphere, it would have been so hot that the surface of Earth would have actually have been glowing with molten lava. I bet the entire surface of our planet was just molten rock that was glowing bright red. That means planets start out hot, but then over time they cool down to have these lithospheres that we know today. The second thing is the differentiation. The process, once the planet forms, of slowly having the heavy material sink towards the center actually generates heat in the form of friction. This is differentiation. And this is why the Earth is a two-part model now with metal in the center and rock on the outside. This is heat from friction. Which, if you think about it, is also being caused by gravity. So gravity is the cause of both number one and number two. The difference is time. This is when the planet first forms, and this is what happens slowly afterwards. Today, planets still maintain heat through radioactive decay. This is heat from nuclear fusion, from nuclear fission. What happens in radioactive decay is that even though only a small fraction of Earth's crust is made from radioactive isotopes like uranium or plutonium, those radioactive isotopes are constantly popping off, and collectively they actually provide a significant amount of energy that flows through Earth. It's where most of our geothermal energy comes from today. You smoke the equivalent of 2 Marlboro cigarettes per year, whether you intended to or not, because of the radioactivity that's all around you. In the state of Rhode Island, most of that takes the form of radon gas, radioactive gas pockets that get trapped in the bedrock, and homes need to be tested for radon gas to see if, you know, you don't want to put your baby in their crib into the basement with the radioactive radon materials, because then your baby will grow an arm out of its forehead from genetic mutations, okay? Let's take a look at how radioactive decay works, because it's kind of cool and you guys might not know that much about it. I can shed some light on this, shed some radioactive light by showing you one of our cool physics Java apps that we like to use from time to time. Astronomy, S drive, physics Java apps. I've got 2. I think there's one on radioactivity or nuclear fission. This one shows you how a power plant works. Okay. So here's basically your fission. Can you guys see this, by the way? Are you seeing my screen? Okay, cool. So you see the little gun in the uranium-235? Uranium-230, why don't I see you superimposed over this? Meeting controls. Oh, there you go. Okay. So Adrian, you can see this, right? All right, all right. Uranium-235 is an unstable isotope of uranium. Did I show you guys my rock of uranium? Oh, okay. We'll do another demo in a second. Watch this. Gonna fire a neutron into uranium-235 and destabilize it. Boom. It splits apart into daughter nuclei and releases energy in the form of gamma rays. What if we add a bunch of uranium-235s? I wonder what would happen then. Uranium-238s are not radioactive, but they're there. And let's add some uranium-235s. Let's see if we can make a chain reaction, okay? So I'm gonna add a bunch. Watch this. I'm gonna hit the U-235, and anytime the neutrons hit another 235, they will undergo radioactive decay as well. This is happening all throughout the interior of the Earth, and it's generating, I think for Earth's case, it's 30 trillion watts of energy is generated through radioactive decay. Now, when we build our nuclear reactors, we have a similar principle behind them. We take all the U-235 out and we throw the U-238 away, and we make these nuclear rods. Now, do you know the Simpsons? This is Homer Simpson's job at the power plant. His job is to control the depth of the nuclear rods so that we can figure out, the goal is to generate enough energy to keep energy flowing, but to not have a chain reaction. Like for instance, if I open up all the rods and I fire the neutrons, that's how you get Fukushima. That's where all of the rods just overwhelmingly fire off and you have a nuclear meltdown and boom, that's it, you're in trouble. If you keep the rods closed and fire the neutrons, you'll generate a little bit of energy, but they kind of peter out over time. The trick is, and it's a little dangerous, but you fire the neutrons and then you adjust the rods in such a way that you maintain a steady but not too overwhelming energy output. See that? This is Homer's job right here. Do you know what we do with the leftover nuclear rods once they're done? We take the spent nuclear rods to Yucca Mountain, New Mexico, or Yucca Flats, and there's a big mountain there, Yucca Mountain, with a big cavity lined with lead and then concrete, and we throw the rods into the center of Yucca Mountain. It's the United States' biggest nuclear waste dump. Now that's nasty, obviously, but most environmentalists are pro-nuclear because while it's certainly nasty to throw spent radioactive nuclear rods into the center of Yucca Mountain, it at least contains the toxic waste. When you burn carbon, it goes up into the sky. And you know who suffers then? Everybody. Everybody heats up, everybody dies, all the little bunnies, all the squirrels, you're all gone. So nuclear waste in the center of Yucca Mountain is paradoxically less harmful to organisms on Earth than carbon going into the sky. That's something to think about. However, you have to know what you're doing. You can't just let Homer Simpson run the job, okay? Anyways, radioactivity is all around us. And we can measure it with Geiger counters, but I'll skip that demo in the interest of time, okay? All right. Planetary geology is dependent on internal heat, not surface temperature. And that's because sunlight hits the surface of Earth and bounces off, but the internal heat has to flow through the interior of the planet. And this is demonstrated by the cooling rate of a planet. And let's take a look at how planets cool off over time. The interior of the planet generates the radioactivity. The rock is convective, so you have convection pushing warm rock up towards the surface. You have conduction, where the heat flows across the solid boundary of the lithosphere. And then eventually, the real way that planets cool off over time is they radiate their light into space. That means planets are very much like hot potatoes on a windowsill. They're cooling off through radiation. Let's take a note on this. planets cool over time. You have convection driving bubbles of rock, and that's in the mantle. You have conduction flowing across rock in the lithosphere. And lastly, the real way a planet cools off is radiation. Planets shine light into space as black bodies. Let's imagine that you're planet Earth. And planet Earth has an average surface temperature of 15 degrees Celsius. Let's see, if you add 273 to that, help me. 273 plus 15 is 289? What? Wow, I'm stupid today. 288. Let's calculate the brightness of the planet. If it shines like a black body, it radiates with sigma t to the fourth. 6 times 10 to the minus 8 times 288 Kelvin to the fourth. Can you tell me what the brightness is from planet Earth due to its temperature? Someone punch that one for me. Olivia, Andrew, Nick, Adrian.
Would it be 412 point?
Yeah.
Like,
Let's just get 400 for simplicity.
okay.
400 what though? I didn't write down the units of the Stefan Boltzmann constant. I was a naughty boy. Do you remember what the units of brightness are?
I want to say watts, but I don't.
It's watts per something.
Oh, watts per second, or no? Meters
Squared.
squared.
In other
Okay.
words, it's how many watts come off of a square panel, right? It's watts per square meter. What about its peak wavelength? Lambda max is 3 million nanometer kelvins divided by the temperature. What do you get if you plug 288 in for temperature, students?
$10,416.
What are the units?
Nanometers?
Good. Can you tell me how many microns that is? How many microns is that? I'm just seeing if there's any fans of the metric system out there. A scientist should be able to convert from nanometers to microns to millimeters to kilometers quickly. What the shit is a micrometer? Do you know? A nanometer, shoot. A nanometer is a billionth of a meter. A micrometer is a millionth of a meter. 10,000 nanometers should be how many microns? How many zeros difference?
3?
Okay.
Yeah.
So how many microns?
I don't know. Would it wouldn't be 3, would it? I'm just
No, it's 3 zeros.
3 zeros. Okay.
Remove 3 zeros.
Oh, 10?
10 microns.
Sorry.
All right. Here's a hint, Olivia. I already knew you were going to have trouble with that conversion. That's why I asked the question, to make you do it.
That's okay. I
regime
appreciate it.
In what regime of the electromagnetic spectrum is that found? Let's get our cheat sheet. 10 microns, 10,000 nanometers. What part of the electromagnetic spectrum is that from?
Would it be the ultraviolet?
Ultraviolet goes from 10 nanometers to 400 nanometers. So no.
Okay. No. I'm not sure. I'm trying to. It wouldn't be. No, I don't know. Infrared? That's not.
Well, where's 10,000 nanometers on this thing?
I'm trying to. No, because after the infrared, that's like it goes to centimeters.
Yeah,
So
this is about 1/10 of a centimeter here. 1/10 of a centimeter. Let's see. How many nanometers would that be? This is a good exercise. So if infrared tops out at 0.1 centimeters, right? Centimeters to meters is 100 times meters to nanometers is 1 times 10 to the minus 9. So do that out. It's 1 million nanometers. How many microns is that, Olivia? 1 million nanometers is how many microns?
would it be 1?
No.
Or no?
3 zeros.
1,000?
Yeah. Hold on. Yes. 1,000 micrometers. Very good. Okay, so 10 microns would be where? Let's go back to our screen. So this,
So it would be infrared.
yeah, that's 1 micrometer. That's 1,000 micrometers, right?
Mm-hmm.
So over here. That makes sense, actually. Planets are like warm rocks in space. Rocks radiate in the infrared. Let's take that as a note. Planets shine infrared light into space, and that's how they cool. They cool because this warm rock is slowly radiating all of its energy into space through infrared radiation. As they cool, their outer layers get colder. I need to erase this. Oh, we never did our final homework problem, did we? Let me write down a key idea and then we'll do that. Here's a key idea. The thickness of a planet's lithosphere is a measure of its internal heat. So the thickness of a planet's lithosphere tells us about its amount of internal heat. If you have a thin lithosphere, like say Earth or Venus, then you have a warm interior, and as a result, you will have lots of active geology in the form of volcanoes and earthquakes. If you have a thick lithosphere, examples of which are Mars, to some extent Mercury, and definitely the moon, that means you have a cold interior and you are geologically dead. And the only type of geology that you're going to see on that planet is usually craters, because everybody gets hit with rocks in space sooner or later. I've got one more note for you here, and then we can do our homework. Adrian, are you still writing? Give me a thumbs up when you're done.
Yes, but you can move on.
No. I'd rather wait for you, because then let's just wait.
No, I've got it.
Okay, I'm gonna erase then. The geology on a planet takes 4 types. There are 4 basic types of geology that we see on a planet. They are known as the 4 geological processes. Now, I need to talk about these maybe next time, but I at least wanted to get this into your notes so that we could start here next time. They are 1, impact cratering, 2, volcanism, 3, plate tectonics. Let's put a side note that plate tectonics is sort of unique to Earth, a full set anyways. and the last is erosion. Together, these four things are the sculptors that shape a planet's surface over time. That's what we'll pick up next time. All right. Let's try to do 49. I'm going to give you the express version. Here we go. Adrian, would you be kind enough to read me chapter 7, number 49? Actually, Adrian, this is called planetary parallax. This is important because it's the story of how we first measured the length of an astronomical unit. And before you read it, let's all draw the picture together. On the right side of the page, I want you to put the sun. And then somewhere in between the sun and Earth, Venus should be represented as a little dot. And then Earth is over here. And we're going to have an observer at the North Pole and an observer at the South Pole observe what's called a transit of Venus. That's where we see Venus appear on the sun like a little black dot. Depending where you are on Earth, you can actually see Venus appear as a black dot either at the top of the sun or as a black dot at the bottom of the sun. And that's important because the two observers compare notes and they can measure the angle between these two dots. I'm going to call that angle alpha. And by alternate interior angles, that's also this alpha. Because I know the true diameter of Earth, I can measure the distance between Earth and Venus using the small angle formula part 2. Which tells me that S, the size of my planet, is equal to the angle times the distance, divided by 206,265 arc seconds. Okay. Adrian, once you have all that copied down, then you can read to us.
Planetary parallax. Suppose observers at Earth's North Pole and South Pole use a transit of the Sun by Venus to discover that the angular size of Earth as viewed from Venus would be 62.8 arc seconds. Earth's radius is 6,378 kilometers. Estimate the distance between Venus and Earth in kilometers and AU. Compare your answer with information from the chapter.
Okay. First thing that I want to point out is that S, the diameter of Earth, is twice the radius of Earth. That's just a basic geometry thing. It's twice the radius is your diameter. So here, this is equal to 2 times the radius of Earth. Now, if I want, I can solve for distance to get distance is equal to 206,265 arc seconds divided by the angular size times 2 times the radius of Earth, giving me 206,265 arc seconds over 52.8 arc seconds times 2 times 6378 kilometers. Go ahead and punch that up for me nice and quick. How many sig figs should I keep, Adrian?
3.
Good. You've learned well. Okay.
4.98 times 10 to the 7th power.
Which is also 49.8 times 10 to the 6 kilometers. 49.8 million kilometers. And if we convert that to AU, 150 million kilometers. How many AU would that be? It's going to be about a third, right? Wait a minute, did anyone else get that? Something's not right here, Adrian. Did anyone else get a different number? Oh, I guess not. Are there any typos here? All right, someone screwed up somewhere.
It's supposed to be 62.8. That's why.
Thank you. Let's punch that in again. Thanks, Nick.
Uh, 41.9 times 10 to the 6th power.
How many AU is that?
0.279.
Now they want us to compare this to the book value, but the book is not going to give us the distance between Venus and the Earth. It's going to give us the distance between Venus and the Sun. So to get the Venus to Sun distance, we do 1 AU minus 0.279. That gives us 0.721. AU. Let's compare that to what we see on Wikipedia. I just had Venus up, right? Oh, crap. How does that compare? 0.723. Pretty darn close, right? Okay. That's our final homework. It's now time for lab number 9. Let's head on over to the lab room. Just a sec, guys. Oh, yeah. All right. So you have this. I've hit all the non-video participants. I'm just talking to the people I am talking to. All right. Let's get out our lunar map too. I'm also going to have us look at a photograph of the moon. I'm going to give you a link to that photograph. It's by HR Astro. Do I have that? saved here by any chance? Let's just see. Yeah, okay. Let me send you guys that picture through the chat log. See if that works. Everyone, look into the chat window. You should see a photograph of a waxing gibbous moon. Do you see that? All right. The purpose of today's lab is not to read the names of the craters off of the map, but to instead use the photograph. So for instance, if you were walking at night with a special someone and you look up at the moon, you could say, you see that right there, baby? That's Mare Crisium. Now you would be a cool person that people would want to get to know. And that's the idea, is can you use the map to identify an actual Maria or feature on the moon? You guys try. What's the name of that Maria? Open up the map and see if you can find it. Can you use this map to tell me what that Maria is? I'm still waiting.
Is it Serenitatis or Serenitatis?
Yes, Olivia. That's
Okay.
Mare Serenitatis.
Oh, Mare. Okay, I didn't see that part.
Mare is the Maria. Can you see my phone here?
Yep.
Mare Serenitatis.
Mhm,
Also known as the Mare stands for sea. That
Yep.
stands for serenity. In the Apollo landing series, they landed here. They called it Serenity Bay. Here's Mare Tranquillitatis. That's Tranquility Bay. Notice, students, that the Maria are much smoother than the heavily cratered highlands. And that makes sense that they'd want to land here where it was much smoother, less trouble for liftoff. Let's get started on our lab here and take a peek at it. Okay, so I've got my Muji pen. I'm ready to go in style. I've got my roll of tape. So some things we can start by putting down here. Put your name. Today we'll be doing lab number 9. And this is AS1010 Summer 2. Okay, do you guys know what the phase of the photograph is here? What's that shape? Oh, wow. That's a cool optical effect. Where's that coming from?
It says it's a waxing gibbous.
Yeah. I should really do this in pencil, not pen. We have to find the crater that's at -20 longitude and +10 latitude. Do you guys know which way latitude and longitudes go?
What? Yeah. Latitude is horizontal and longitude is vertical.
Right, but here's something to think about, Olivia. Even though latitude is horizontal, the lines measure north to south, right?
Yeah.
And longitudes are longitudinal. They're like this, right? Like tangerine slices. But they actually measure east to west. You see what I mean?
Yes.
On the map, Olivia, things are a little weird because this map was probably made with a telescope. On Monday, you remember we built a telescope and everything looked upside down. So positive 10, this is 0 degrees latitude. Positive 10 is here for latitude. Negative 10 latitude is there. Okay. Can you guys use the map and find me the number of the crater? You find the numbers, and the numbers can be looked up here in the key. What's the number of the crater at minus 20 and positive 10? Use your map and tell me what you find.
I'm sorry, what was that? My dog was begging at my door.
We are looking for the number of the crater, Adrian, which is at negative 20 longitude, but positive 10 latitude. And you're using the moon map that's provided in the lab section today. We're not moving on until you find it.
I think I got it.
I'm sorry?
I think I got it. Is it? Hold on. I gotta find the name of it.
Who's talking right now?
Nick.
Oh, Nick. Yeah, what do you think?
Is it number 43? Bond plan?
No. No. How did you get that? Oh, it's not number 43. Nick, look. You've made a mistake. Negative latitudes go up. Positive latitudes go down. Shoot, you can't see my pencil here. I don't know what's going on. That image is frozen right now.
So it'd be 74 then.
It's exactly, it's 74. It's right here. Can I draw on this? That's minus 20. That's positive 10. Olivia, can you see my drawings? Okay. And what's the name of 74?
Copernicus?
Yeah, I don't, guys, for some reason, my screen is like, oh, there we go. All So let's do this. I'm switching over to pencil for good judgment here. Now, we want to pick some Maria that are actually visible in the photograph. So what I'm going to do is I'm going to kind of do some good feng shui where I superimpose the photograph over the side of the map that I can see. So can you guys give me some 5 Maria that we could see? Maybe it could be like 1, 2, 3, 4, 5. Maybe those. What are the names of those Maria?
Mare Serenitatis.
Serenitatis.
Serenitatis. Mare Tranquillitatis. Mare Nectaris.
Yes.
Mare Crisium, and I can't pronounce the last one for the life of me.
Fecunditatis. Let's make sure I spell those right. Oh, there's 2 L's. Tranquillitatis. Fecunditatis. And Crisium. Now the mountain ranges are kind of, oh, hold on. Give me thumbs up when you're ready to move on. Okay, nice. The mountain ranges are interesting. I want to show you guys something on these maps here. Look at my photograph. Do you see how, look at one of these craters, okay? And you'll notice that the shadow on a crater is on the left-hand side. That's because the crater is an intrusion. These are mountain ranges, they're extrusions. Notice that the shadow is on the right-hand side. By noting the direction of the shadow, you can figure out whether your doodah is popping up or pushing down in. So the mountain ranges on your map tend to look something like this. They're reproduced here, and they have letters on both sides, D to D. And this is one of the mountain ranges that's present here. If we go to our legend, we see that we are dealing with the Apennine Mountains. So that could be one. This could be another one right here. Can you guys tell me what this mountain range is? Using the map? What's that mountain range?
Would it be the Haemus Mountains? Or H-A-E-M-U-S?
No.
No.
No, I don't believe so.
I might be looking at the wrong thing. I'm trying to read the...
Well, where do you see letter I? I don't see letter I here. On my map, there's J, K, where's I? There's H. T. You're supposed to look at where the mountains are on the map, right?
Yeah, I'm trying. I'm just having a hard time kind of reading the map. I don't know if it's because it's the way it printed out on my end, but just trying to figure out where everything is.
Yeah, I mean, well, reading maps is kind of an art form, right? And it's a lost art that we should try to learn. It's just, normally you could try to go to the same place on the map where you see the mountain range. Like this is the Apennine Mountains. What do you see just below and to the left of it? I don't see any there's the Apennine Mountains there, right? D to D. I don't see no damn letter I anywhere.
Is it the Caucasus Mountains?
Caucasus Mountains, I believe, right?
Caucasus.
Caucasus Mountains, F to F, yeah. We could just pick like this stuff here for our third mountain. What's that look like? I think those mountains are maybe B to B. The Alps. Okay. Get my tape out here. Just a second, students. Sorry, guys. Oh, here we go. I got frozen screen again here. Come on, dingus. Start. Oh, there we go. All right. We have to identify three different types of craters. There are flat bottoms, central peaks, and rays. And I'll try to describe what each of them look like. Sometimes craters at their basin will kind of have a flat, smooth bottom that looks sort of uniformly shaded, as if it was maybe filled in with some kind of a lava or something. Sometimes that's a flat bottom. Sometimes the craters have a little mountain in the center called the central peak. That's from where the kinetic energy was so high that it liquefied the rock and created a kind of slapback, a wave phenomenon that created a constructive node. Basically, a little bit of the rock slapped back from the momentum of the collision and froze in that shape. And the third type of thing that you can see sometimes surrounding craters is if this is the basin here, whether it's peak or flat bottom, you can sometimes see rays sticking out from the crater. And this is the ejected material that got kind of kicked out. Unfortunately, as you get farther and farther away from a crater and you look at it from outer space, the rays can kind of blend together. And on our map, the rays are just going to kind of look like the smallest amount of discoloration. Okay, so let's take a look at this guy here. That's what I would call a classic flat bottom. Can you guys identify that on the map? Find me that crater.
Were you pointing at Aristellus, or however you pronounce that?
No. It's close. You're close, but here, let's do some crater hopping together. Do you agree, Adrian, that these are the Apennine Mountains? A yes or no will do.
Yes.
Okay. Sorry, you're not in my little window box. Maybe you tried to nod or something. Okay.
I did.
Yeah, you were below the faces that I could see. Sorry. Okay. So we have 1, 2, 3, and this is the big one. And I believe that's 1, 2, 3. You see? Because there's your Apennine Mountains,
So it would be number 14.
which is Archimedes. Now that you mention it, that guy looks kind of like it's got a flat bottom too. So why don't we use yours as well, Adrian? And that was number 17, Aristillus. Or Aristilius. Oh no, Aristillus. This is another classic flat bottom here. Someone help me find that guy. Who's got the map chops?
Plato.
Very good. That was number 230. Number 230 is Plato. Excellent, excellent work. Central Peaks. There's an easy to spot Central Peak. Can you guys see a little dimple in the center? What's that, dude? Oh, sorry. Wow, we made a mistake earlier, didn't we? I messed up, Adrian. This is actually number 17, and that was number 22, wasn't it? Do you see what I'm saying?
Yeah.
Oh, do you want to know what's cool? Remember Monday night I saw you guys? I actually went out Monday night and I did some observing. I have no idea Let's hope all these photos are PG-13, but okay. So this is, I set up a telescope. This is me just showing a slideshow. I just remembered that I took a bunch of pictures on the moon. My friend who was observing with me took this kind of filter photograph of me all sweaty setting up the telescope. This is on the roof of the Peerless. There's Jordan looking through the telescope. It was really fun. Just for fun, we looked at the Independence Man. But check this out. I got some, this is through the Finder scope. I watched the moon setting, but I have some really nice, those are my friends, Adam and Alexandra. But here are some images of the moon, and you can actually see some of the crater. Look, you can see the Apennine Mountains right there. So I was just doing this the other night. This is, I guess, what astronomers do for fun, right? Anyways. I just realized that it would be really easy for me to go into my photos and show those to you. So why I was thinking about that is, hold on, do you see the mistake we made? That was crater 17, and that's not a flat bottom, is it, Adrian? So let's move Aristillus over here. Or Aristillus, all right. Good thing I switched to pencil. That was the one that I meant to refer to. Which crater is that, students? Actually, look, the reason I thought of this is rather than do that one, let's do this as a flat bottom. I observed that the other day through the telescope very clearly. And I told myself that when I did this lab with you guys, I would try to remember the name of that crater. That's number 239. I know which one it is because I call it the snowman because you can see 3 craters in a row for the snowman. And that's number 239. Ptolemaeus. So that's going to go in place here. Meanwhile, I can see the snowman has a nice central peak right there. Notice the shadow is on the right-hand side. And this crater here also has a central peak. Can you guys tell me the name of this crater here at the end of the Apennine Mountains? What's that dude?
Talking about 17, right?
No, 17 was Aristillus.
Oh yeah. Okay.
I'm talking about the one that if you follow the Apennine Mountains is right at the end, because that kind of looks like a central peak to me. Come on, guys, work with me here. I'm going to show you the pre-recorded video. You're one fucking step away from getting the pre-recorded video.
Is it 22?
22 was the thing that we confused for a flat bottom. That's 22.
Oh, okay.
I want this one.
Oh, okay. Hang on 1 second. Let me go back.
Eratosthenes?
Very good. Do you remember that we studied him earlier in a homework problem? That was the guy who measured the circumference of Earth with 2 sticks. Crater 97 is a flat bottom named Eratosthenes.
Can you keep the camera on the first 2 for a second? The first 2 columns?
Oh, yeah.
Thank you. I'm sorry. I guess I fell behind at some point.
That's okay. I don't mind. Here, let me, hold on a sec, bud. If I hold this in this little doodad, see, it's hard for me to hold it steady with my hands, so. There we go. Who's cooler than me? While I'm waiting for him to copy that, you know, I used to pronounce this Eratosthenes. And one year I had a student who had studied Latin in the Boston Latin School, and she took me aside after class one day and she went, "Psst, it's Eratosthenes." So I've always made sure after that to never refer to Eratosthenes as Eratosthenes. It's hard to know how to pronounce some of these old-fashioned names. But
Thank you. I'm sorry.
you're welcome, Adrian, no problem. That's one of the cool things. I gotta say this. You know how like when you have to go to college, you have to take languages? Well, I always really object, like an idiot, because I was an 18-year-old dum-dum. I objected for some reason to taking languages, as if it's not cool to know how to speak a bunch of different languages. But I made a big show out of it being, oh, this is a waste of my time. So what I tried to do is I tried to take the most archaic, most useless language I could think of, which of course was Latin. And I argued to myself, well, at least I'll be able to read some cool science terms. But I didn't realize what I was wading into, because the studies of the classics are so cool on so many levels. First of all the students who were classics majors, they would just sit around in this library reading like Catullus and Seneca to each other. It was so stylish. They would just sit around. They were always chill and relaxed. And my professors were archaeologists that would just come back from a dig in some exotic locality and had pulled up some pottery shards. And listening to them speak Latin and learning to read the words of the ancient Greeks and the ancient Romans was so cool. It was just so awesome. So classics are a surprisingly cool branch of academic study that you wouldn't realize how many weird areas of life it connects to. All right, that was just me yapping while people were copying. Let's get our last, let's go back to this snowman-like feature here. Wait, hold on. You guys are taking up too much real estate. 1 second. Let's go back to that, hold on. That snowman-like feature there. And I was thinking that could be a good central peak to get. What's that crater? Arzikel, maybe? Yeah, Arzikel. Very good. That's 19. Arzikel. Crater rays are going to be kind of tough. Can you guys see how this crater here has some like gray splatter around it? I believe that those would be considered crater rays. I believe so. That crater, let's look at it again, is in this Maria, which was called Mare Vaporum. I think it's 187. Oops, sorry. Oh, there's the eye mountain. Technically speaking, those eye mountains were visible. 187 is our boy here. Manilius. Manilius. We should check and make sure that there are actually crater ray systems. I don't want to turn off my phone because you know how like sometimes I don't get it back. Let's look up crater Manilius. Manilius crater. Let's make sure Wikipedia will have some extra details about them. Let's make sure that's a system that has rays. There's definitely some stuff around it. I don't know if that would constitute as rays. Crater rays look pretty, they're hard to see depending on the angle of the sunlight. This photograph might not be ideal for, okay. This is just a classic example of crater rays. Do you guys see that right there? And that's a crater on the moon. I think that's, oh, what is that? Damn it. Bear with me, students. What is that crater? I've seen that one before. That's definitely a crater on the moon. Oh no, that's on Mercury. I'm dumb. Okay. Here's a crater ray system. What's this? That's Kepler. Let's see if we can reverse that. Do you guys see that ray system there? Do you see how you can literally see all the material that got blasted out of the crater? Pretty cool, right? Look at all those spokes radiating it. That was all the rock that got vaporized. Let's see if we can find Kepler, the Kepler crater. We're going to go in reverse now, okay? Reverse means it's going to be trickier. So we'll find Kepler. It's alphabetical. This could be a fun exercise. Kepler is 155. Oh, geez Louise. Can anyone find crater 155 in this mess? There's kind of no rhyme or reason to it, but maybe all of us looking together, we can crowdsource it. One of us will find it first, right? I'm hoping it's me, because then I win. 155. Who can find 155? I've got an idea. We can cheat. You want to know how to cheat? Let's look up Kepler on the internet, and it'll tell us what quadrant it's in. Sound like
it's,
oh,
sorry, I found it.
damn you. Okay. Sorry.
Oh, no.
No, congratulations, you. Did you find it?
Sorry, I found 255. Apologies.
Yeah, I found 255 too. I got excited. Keep looking. I'm going to look for Kepler here. I'm going to type Kepler crater into Google. Kepler lunar crater. Oh, it's going to give us the coordinates. 8 degrees north and 38 degrees west. I'm not sure if north is positive or not, but. It lies between Oceanus Procellarum and Mare Insularum. Oceanus Procellarum. Oh, maybe it's not on this side. Oh, boom, I found it. You know what sucks though? That's not actually in the photograph. It's too dark. It's out past Copernicus. Let's put it down since we did so much bloody work on it. Okay, can I get a simplified ray system, please? How about that? Wait. I don't know if that's just some gray stuff or if that's some rays, but let's pretend it's some rays, okay? What's that guy? Actually, does it look like he has crater rays? What's that? That's 283. And then those two are 4 and 121. 121 is Godin. Let's just check out Godin on Wiki for a second to see if it's a ray system. You know, every time I do this, I try to do something different just to learn for myself. Godin crater. It's cool. They have all these different views. Like here's an oblique view from the north. That's kind of cool because you can see the depth of the crater. Nah. How about this one here then, the original one that I suggested? That is right near Mare Vaporum. It's 187. Manilius. Let's look at some images of Manilius crater. Well, there's definitely some stuff splattered around it, right? Can you guys see that? I'm going to call that crater rays. Maybe not the best races. Oh, wait. Shoot. I already did Manilius. I'm so dumb. Okay. How about this guy here? What's that guy? Oh, I see what I did wrong. I got the wrong crater. That's 187. This guy is just above in Mare. That's the sinus meaty. That's 283. I apologize. 283 is Tri-Snicker. Tri-Snicker. Let's write him down. I'm curious. I don't know about you guys, but I'm just curious. What would you say? Does that qualify as crater rays? Looks pretty gnarly, doesn't it? I'd give that a, hey, that's a ray. Or something. That's a pretty wild looking photo, actually. You know, you always forget, just like the moon is really amazing. And there's so much cool stuff to see. Look at that beautiful photo. Cool stuff. All right, let's move on. The crater rays are always really hard. Here's what we're gonna do. We're gonna skip this section because I'm dallying and I'm taking too long. We'll do this section. We're gonna do the scale of the photo because this is really important. You know, when you see one of these craters, like, do you guys remember this one? This is Crater Plato. When you're looking at an aerial photograph, it's kind of hard to know how big this thing is that you're looking at. Is this the size of a Chihuahua or your backyard or the state of Rhode Island? How big is the state of Rhode Island in kilometers? Does anyone know? You live here, we should know. How would I find out? I would just type Rhode Island into Wikipedia or the internet. And then I would go to this corner it'll give me the dimensions. So Rhode Island is 77 kilometers by 60 kilometers, okay? So there's our reference. How would, oh shoot, I stopped my share, I'm sorry. Let's pray to Phoebus that this thing works. All right, good. Okay, here's how we would do this. Over here, I want you to write the true diameter of the moon. 3476 kilometers. That's the diameter of the moon to 4 significant figures. My thinking is we'll go to the photograph of the moon and we'll try to like measure its diameter. We'll measure its diameter as some number of millimeters. And then we can divide the true diameter of the moon by that to get something that we call a scale factor. A scale factor is what I use for a map to determine how many kilometers are in 1 millimeter, right? So let's do that with my ruler here. I'll make sure to put 0 right at the bottom. And then up here at the top, I'll measure. What would you say is the diameter of this moon in millimeters?
$225.
The 5 is the big tick mark, which kind of looks like it's out in outer space. I would say 224, Adrian. Do you see my beef there? Can you see how the 5 is just a little bit here in outer space, but the
Yes,
4,
I see.
yeah. I mean, I'm sweating a millimeter, so it's not a big deal, but let's go with 224. Can you guys divide that up for me? How many sig figs are you going to keep?
3.
Good. Divide it up. What do you get?
$15.5.
What are the units?
Kilometers?
Uh-uh.
Kilometers per millimeter.
That's right. Now, what I can do is I can pick some features, like that crater was called Plato. Let's also pick this guy, Mare. Well, we'll do the Apennine Mountains. And then we'll do Mare Serenitatis. And the idea is if we measure their lengths in millimeters, we can multiply that to get their diameter in kilometers. So let's do that with crater Plato. I'm trying to get this at the right distance. What would you say for Plato?
7.
7 is definitely past the edge. I'd give you, I know it's hard to see, I'd give you 6. 7, I think, is pushing it, okay? Is that okay if we change it to 6? Yeah, obviously, Adrian, it's very difficult to see through this crappy, you're looking through the Zoom, through the internet, through my lens, right? It's all messed up. Okay, now, Adrian, multiply 6 millimeters by 15.5, and what do we get?
$93.
But how many sig figs can I keep?
1.
Because our measurement was only good to 1. So what do we want to round it to?
90.
Good. How does that compare to the state of Rhode Island?
Bigger. Or
You would-
smaller.
you
I
would
forget
tell me-
the measurements of Rhode Island.
So Rhode Island could fit inside that crater?
I don't remember the measurements you gave us for Rhode Island.
Right there.
Apparently, yes, it could.
That's pretty wild, right? So it'd probably take you a long ass time to walk across that crater, wouldn't it? Can I tell you why this kind of blows my mind, Adrian, and freaks me out? Imagine if you were one of those Apollo astronauts that like landed in Mare Tranquillitatis. One of their jobs was to ride in the lunar dune buggy out to the highlands to see if they could measure the radioactive dates of rocks out there. But it's got to be scary enough to land on the moon because there's no mission control, there's no water parks, there's no sandwich shops, right? You're kind of just effed if something goes wrong. Then to imagine taking a trip a distance the size of Rhode Island and you're on the foreign planet, you know what I mean? That's got to be freaking scary as hell. I don't know, it makes you think about how cool and brave those astronauts must have been. Okay, let's try the Apennine Mountains. I'd say they end somewhere around there. I mean, it's curved, so it's not quite fair, but let's say 30. Hold on, I can see better than you guys. Actually, the dark shadow of it goes all the way out to 35. So let's keep it simple and make it 35 millimeters. Can you guys calculate that in kilometers now? Just multiply by 15.5.
$542.5.
Well, hold on. Okay, Robo, like that's too many numbers for me, right? How many sig figs, Adrian?
2, so 540.
Okay. How about Mare Serenitatis? You guys want to just go with 45? Well, I don't know. 43. Again, 2 sig figs. 666, except 670, right? Imagine if you had to traverse one of those Marias. That could be like traveling across Texas. That'd be a hell of a journey. Okay, I'm calling us dunsies. Does anyone need to look at that one more time? That was lab number 9. I've been keeping up with the grading somewhat. You'll notice that I've been keeping a running tally of grades. Has everyone been good and kept their work coming in? No slackers, right? Good. I want us to finish nice and strong. Did you guys figure out how to look at your grades yet? Or did I not really tell you how to do that? You were able to look at them, right? I think I graded them. You should be able to see them in your grade center, I hope.
I don't think I've seen it. Let me check now. I think I checked yesterday.
Yeah, Janet Belt. Take a look at that. Otherwise, I can try to figure out. I think I can chat you your grade individually if necessary. I forgot. I can chat to.
Yeah, mine's not showing up.
Yours not showing up. Janabel, I believe I can send you your number privately.
Yeah, mine says 0 on it too.
What? All right, so this is, oh, sorry, this isn't, I gotta plug in my number pad. Wait a sec.
The midterm, you mean?
Yeah, midterm. Does anyone see theirs? I graded them, quote unquote. Okay. Janabelle, I just sent you a hi. Did you see that?
Where did you send it exactly? Not in my email. Is it
No,
still
to
Blackboard?
to your chat.
Okay, one moment. Okay.
All right. Everybody should be passing the class C or better, as long as you're doing all your homeworks, okay? So don't freak out if it's not everything you hoped for. Oops. Sorry. It doesn't look like Matthew Lonnie is missing homework. Paige, sorry, Ernest Page, you are missing.
Yeah.
You are missing homework 4 and homework 5. What's up with that?
I submitted 5 actually earlier today, so that one shouldn't be missing. But
What
4,
about,
yeah, I am missing that.
what about lab 6 spectroscopy?
I submitted a bunch of stuff today, so
Okay, all right.
it
Well,
may
I didn't
not have
grade.
updated.
That's cool, man.
Huh?
Look, I didn't grade today, right? I graded on Monday. So if you submitted,
Okay.
cool. But you still owe me homework 4. If you want to go back and do that,
Yeah.
are you willing to do that?
Yeah, could you possibly email me the video, because the one that you have, I don't know, I think it was like you only had like the last homework problem like in the video. I think you forgot to record or something.
That was the day I forgot to hit record. Luckily,
Yeah.
Ernest, I do have a video from summer 1 that I can share with you. Hold on a second here. And Ernest, I will send you your grade privately to chat. Wait a sec here. What was that? That was homework number 4, right?
Yes.
So here we go. So copy, shareable link, chat. Where's that chat window? Oh, there it comes. So here I'll select Ernest and paste. Did you see that?
Yeah.
All right.
Okay, perfect. I'll do that today.
Sure. Do we have other stuff that we need to talk about, students?
I don't have my exam grade either. I don't see it on Blackboard.
Okay, I don't know why. You'll have to forgive me. I don't know what I'm doing. I really got to consult someone who does. Like I just barely managed to give you the test, and it did grade it, but for some reason my 1020 students. Ernest, are you still here?
Yeah, I'm still here.
All right. So that's your exam score. And let me flip to Olivia. It's Pachinko, right? Is that how I say that?
Pacino. It's Portuguese.
Sorry. Okay.
No, it's okay. It's weird looking.
I like it. I like weird looking things. Okay.
Thank you.
42. Okay. So remember to divide by 92 to get your percentage. And then basically mix it in with your homework score and your lab score, and it should be good. Once again, students, if hypothetically, let's say you have a 50%. If you add that twice, once for homework, once for midterm, once for lab, but if you do 100% on homework and 100% on labs, that's 3 divided by 4. That's a 75%, which would be a B+ in my class. So you can get a 50 on the exam and get a B+ in my class by just doing all your homeworks and labs. So if you guys aren't too psyched about your grade, just make sure you get all your homeworks and labs to me. That's why, Ernest, I'm making such a big deal about not missing a single one. You know what I'm saying?
For sure. Yeah, I appreciate it. Thank you.
Yeah. I very rarely have to fail a person or even give them Ds. That's the only time people get Ds in my class, or God forbid fail, is if they miss many homeworks and labs. And none of you guys are in that position, so you're all on track, okay? We're all doing it together. It's going to be fine. And if you need help computing your grade individually, I can show you how to do that. Okay, cool. So I guess that's it, right? Adrian?
Sorry, may I please also have my grade? I can't see mine either.
Sure. I'm so
Thank
sorry,
you.
guys. I don't know why it's that's happening. So, and Nick, do you want to see as well?
Yeah, why not?
Adrian, what's your last name again? I forgot what.
Chevalier, it's
Oh, right, right. Yeah, I understand. Okay. Yep. Adrian Chevalier. Okay. Oh boy, I'm stupid today. Yeah. So, okay. And Nick, it's kind of cool that I can kind of chat you guys individually. There's some nice aspects to this. Where are you? I know not everyone's paranoid or secretive about it, but just in case, so you're all in your comfort zone. All right.
Are we good to go for the day?
Yeah, I guess that's about it,
Okay.
unless you guys have any other questions for me. Who are the, Destiny, Janabelle, I don't know if you're in the background there.
Oh, we're all set here. Sorry about that.
Janabelle, do you want me to, did I send you, I already sent you yours,
Yeah,
right?
you sent it to me and I calculated it. Thank you.
Yep, okay. Destiny, I don't know if you can hear me because you're so quiet back there, but I can do it for you too. All right. Otherwise, I guess I'm just going to end the recording and I'll see you guys next time, okay?
Thank you.
All right. Peace be with you. I'll see you on Monday, okay?
Thank you. Bye-bye.